welcome.
Okay, let's full screen it. Oh, nice, Gonzalo. Yeah, let's read this one. Anyway, yeah, Wildfire published a bunch of stuff recently. I just picked this one because it seemed like an actual paper, where other stuff they published were recently were blog posts and didn't seem that interesting. But yeah, I mean, if there is something better that they published recently, you can also tell me and we can look at it another day. But yeah, let's look at this one for now. Yeah, as usual, like people feel free to talk at any point. Like by default, I'll go through the paper myself. But it's better if people actually talk and discuss stuff, even if it's just saying, commenting something on the text chat if you don't want to actually talk on voice.
Yes.
Also, for the people who joined, next week it might not be on Monday because we have the authors of a paper who want to present, and they are not available on Monday maybe. So I might switch to Wednesday, but I'll try to announce it with some time before.
Okay. Yes.
Yeah, let's go get to the actual paper. Everything is working. Let me check that we're actually streaming correctly to YouTube and all that. Okay. It seems to be working. Anyway, so no presentations carry rich geometry structure, but not so it seems it has with interventions that respect geometry. Okay, so this is about they have all of these shapes that people find on models, and to some extent people are already doing this on the papers when they find the structure. Some people have already done causal interventions, but I guess this is more a more general thing where they have a bunch of assumptions about taking a bunch of geometric structures and then do steering to see if they are causally relevant and if the results make sense with that. Manifold steering, yes, behavioral stories that follow while linear steers with including geometry could through of manifold ranges and senses produce natural outputs. Okay, so they have this manifold steering.
And also they have code. That's nice.
One thing I keep on thinking, like, when would the structure would form underneath? It's like during the start of the training process, but at the start, the layers accumulate lots of gradients and the main infos about what the task has been trained on, and then in the later layers we see that it deviates a bit. It's like the performance decreases a bit. So, like, I was thinking, what do you all think? Like, where at what layer stage the main geometric structure could arise, where they are capturing some concepts as given here?
I think it depends on this exact structure. Like, for instance, if it's more low level, then it's in more earlier layers. If it's more high level, then it's in later layers. Which isn't the rule always, but that seems to be the heuristic, at least approximately. I think, if you like look where all the different features are located in the different models at what layers.
So for easy task, will it be in the earlier layers, and for like more difficult task, more later layers? What do you think?
Yeah, I
think
think
it
that's
depends.
likely also
Like
the case.
it could be the case, but I think it depends on. Like, I think it's going to be more complicated than that.
Yes.
Like also about abstraction or whatever.
Again, I'm also speaking from intuition and heuristics. Like
Yeah.
no math has been done yet.
Yeah, like I would like if it's a circuit that needs some low level patterns, those will be first better match in the error layers. I don't know, curves for instance, and then can be composed in later layers into more complicated structures. My intuition right now is coming mostly from the CNNs, but it was
I
also
mean,
found
yeah, in
in
general,
the LLMs.
if something requires multiple layers, it necessarily has to be not on the first layer, right? At least.
At least
Yeah.
the mid layer.
I mean,
Yeah.
there could be things where it's actually something complicated, but that it uses multiple steps. Like it only happens on some long text where it's actually going through multiple forward passes or something. Although it's hard for very complicated things to be done there because of the there is not that much there's a big bottleneck on the tokens. Anyway, going back to the paper. Reasoning tasks with
Also,
Hmm?
I would expect also like that some tasks would be like through shortcut learning, like almost memorized, and some tasks will have like some more complex circuits instead, depending on how well it's trained. So I would assume the pattern matches are mostly in the earlier layers.
As far as I can recall from normal deep learning, mostly if there was like very much complex data and less training and more complex data, or like less training done for like less epochs, so the model would tend to overfit again. It's like memorizing what you said. So can we connect this with what we are discussing here right now? Like, maybe, or take some intuition at least.
I mean, if you want to look at the training dynamics, there are some papers that are trying to look at the training dynamics of how the features form as you train. Like that first you get statistics, that the like just co-occurrences, that then you get like more complex features. The one paper I'm thinking of didn't study this, but I would assume then later you get like some more complex circuits, and also there's stuff like crooking, but
Yeah.
and induction heads, but it depends on the model as well, how much of it
Okay, so
happens.
Victor got distracted. Like let us let's
Okay, let's go back to this
Don't
paper.
worry. I was also just reading the thing in the meantime, but not paying that much attention. I was okay. So just going to say that. So this talks about. So the idea is that the the geometry in the neural representation is not incidental, but is in fact the property for controlled via intervention internals. Like that, the idea is you need to find the right geometry instead of the right direction. Although at the same time, like finding the right direction, some like often works okay. Like a lot of I guess you can see that as a lot of the geometry of different features are just approximately just a direction. Uh, Even like even a lot of the structures here, like if you have this circle, you can still approximate the position of a number by yeah, it's still a direction. I guess it might be a thing where
Those are days of the week, and then
yeah,
months.
like each day of the week even if yes, there is some sense if you there is some steering you can do in the time dimension where you do a rotation on this circle. Each point is still a direction in some sense, and that I guess unless you find some example, like I guess the thing you need for directions to not war is that there are some examples where the like a point here means I don't know if you can see it. I probably shouldn't do that kind of thing because people who are just hearing probably won't notice. But like if you have some point where the length of the line matters. To some extent, that's true. That if you do steering, you have to pick carefully the strength of the steering. And if you do it too much, breaks. Although that's probably also because the steering is not in the exactly the right direction when you are adding other stuff that breaks things, and also
Yeah.
the norms matter a bit. That if my very high norm is going to break the layer norm or whatever. But yeah. But
I wonder
But
how
I
does this
think
compare. Go ahead.
okay. No, I was thinking that they have tested this in a fairly easy task where like trying to speak of the next date. So the structure, I mean the geometric structure of the manifold is also pretty simple, I think. Or if we introduce more complex tracks, would the directions would be a bit more different or at least not that straight? I mean,
I think the
or
problem is
am I speaking wrong?
yeah, no, I think it's true. That's stupid. We don't actually know. Like, I think all of the examples seem maybe they have some cool, more complicated examples, but I think most of the examples we know of are actually not that complicated. The geometry is not that complicated. Except maybe the geometry, but most of the other things seems to be like circles or some kind of curve.
Like,
Maybe more
or
dimensions, but it's still a curve.
like at the same time, the line breaking circuit seems to be the geometry of the line breaking circuit seems to be more complex. Like it's as far as I know, that's the most complex circuit I've seen so far.
I mean, but it's still that's still a curve, right? Like it's like each number is still a direction on the space too, and it's just
Yeah,
it's curving 6 dimensions, but it's not like
but the fact how it's all composed together, like all the all the different sub circuits, essentially
oh yeah, but that seems like
feeding each other.
separate in terms of like I was thinking just as the composite of the representation, but yeah.
Okay, I see. Like if you would wanna steer this, then like you need to steer all the different aspects in
Not
some ways
really. I
together.
think you can like if the number is represented in the spiral thing, right? So in the curve, you can steer it by putting another number on there with the right direction. You don't need
Hmm.
to know how all of the other mechanism works. You just need to know the part that represents the number and do an intervention on that. That's basically just a line.
And the
Okay,
rest of the circuit would follow from that edited
Yeah,
number.
I'm curious. The paper maybe has some examples where they find things that where their method is better than other stuff. So maybe it's cool. And
when I
there's maybe.
read,
Mm.
oh, sorry. No, finish, and I will
Oh yeah,
speak.
I was just saying. Maybe there's probably more complicated structures. It's just that we haven't found them yet. As I said, for some reason, it's kind of a problem. I mean, maybe it turns out. I don't know. Maybe it turns out just doing even if it would in theory be better if we actually understand all of the structures. Turns out in practice it just
Yeah.
works fine to just assume everything is linear and to find the right direction. Like and,
I won't. At the same time, I wonder if this in this paper they found some like if you compare linear steering to this manifold, this curved steering,
yeah.
which they I think compare. Like so you get better results, essentially better steering, since you don't go out of the manifold too fast. I
Yeah, I think that
think. I
that
don't know.
could be.
Okay.
We seems like to
Yeah.
that. We'll get to that, I guess. I'm switching to
Also,
getting
yeah.
to the next
I
thing.
had one question.
Yeah.
Uh, when I read, I I got their intuition behind the geometry of the manifold. Okay, it's fine. But what do you think about the like behavioral signal as they were speaking of? Like, how would it be more efficient than just steering? Or like, yeah, steering. The because in the intervention you can see they are steering into the geometric side, and for the behavioral signal, I think they did something. Anything else? Like,
So I guess I'll have to read that part of the paper because I
Yeah, I also have to read that.
yeah, I haven't read
but
the
I mean, by the diagram, I was just trying to think. Okay, like,
I
Yeah,
don't know.
those.
We'll see. I wanted
Also,
to
yeah,
comment something about this introduction first, but yeah, we can get to that after.
like, oh, yeah, like what I kind of wonder is that you have like, I don't know, a happiness direction that you can steer. For instance, you have these numbers directions on which you can like go on the lines and on the light on those or circles here. So I really wonder if there's something like, I don't know, some algorithmic, as in like, I don't know, identify position in the line versus identify end of the line. If those two also live on some shape, and you could like steer on that shape across some like algorithmic state space or something like that. I don't know. That's something I'm wondering if yes that exists or not, or if it's just too disentangled. I don't know.
and I think we must not forget about how much data in itself alters the training dynamics when we train. Like, we can
Yeah,
have
definitely.
exploding gradient or vanishing gradient, like, and I think this might have effect, or I mean little effect on the linear lines or what they have here. I mean, again, they use fairly simple data, right? So we don't see anything here right now. But I was speaking of when we have more like real world complex data.
Yeah, like this is definitely the case that the data in very big part forms everything that's happening inside the neural networks. Yeah, I agree. By the way, Victor, can you zoom it a bit in
Oh,
for the
yeah.
live stream? Yeah, okay. Yeah, that's readable.
I removed this. Oh, okay.
Yeah, I think you can. You can on top the. Yeah,
Okay.
that's okay.
Probably better this way. So, oh, I was going to say that on the also one side left, but never mind. Lemon. So I was going to say that here they talk about recent literature has begun to identify the origins of these structures by attributing them to what the statistics shape by conceptual structure, but like this relates to that paper that we read that was saying that this was about the statistics on the data. I don't think that's exactly true, something a kind of trivial sense in that everything is about statistics in the data. In that, that's a reason why you can see these representations, but it's not the only one. It can be that there is some task so by this I mean, so if you want to represent things that happen often together, like closer, you are going in some space. You are going to have to make some, some curve shape, like the ones on here, right? Like if you want to, we saw that paper in that it showed like how if you want to do word embeddings or whatever, and you want to embed things in a way where uh, each day of the week is closer to the next day of, to the day of the week that are adjacent and more separate from the others, but the last day is connected to the first day, you have to make a circle like this. This is also related to if you want to have like cosine similarity between each thing.
Yeah.
More similar when it's closer. Of course, you make a circle because that's like like in 2D, it's cosine similarity. The things are more closer there. The closer the thing is, and this relates to how if the model wants to get to access some data based on some linear transformations, it makes sense that it's taking some line here. But I mean, it makes sense that a lot of structures in models are the kind of thing that I was saying that you can find with a linear transformation, because that's, for example, the kind of thing that you can use attention to pay for because it's linear. To pay, to look at, you have attention, look at some, I don't know, you want to be able to, for attention to look at numbers that are more than whatever, whatever number, it has to be in some way that you can access linearly. But the anyway, so what's I'm saying? So there is some sense in the Bigelow structure of the data can make this shape, but I don't think it's the only reason you get this shape, because, for example, the transformer thing, like the line breaks circuit thing, is not an example of this. It's an example where the model learns some computation that was useful for something else. That's when to put line breaks, and it's, or you have an example with models doing modular addition. It also says the same kind of structure, and that's not because of directly the statistics of the data. Although it, in some sense, it is, because everything that models learn, you can say, is for statistics of the data, but that is kind of meaningless. But it's because it's learning some algorithm where representing the data in that way is useful, and that's more about, in some sense, the structure of, like, it's just the model wants to represent a one-dimensional variable, and the nice way of doing that is with circles on inside activations or whatever more complicated curve. But yeah, anyway, let's go back.
That makes sense. Or,
No,
like
it's
I would expect in something like Alpha Zero that there would be some shapes which, since it's trained via adversarial self-play reinforcement learning without any like ground truth data really, and that in there you could potentially find some stuff, some non-trivial shapes potentially. I'm not sure. I think
you should still find shapes there, even though there is no data to. I mean, there is data, but even if it's just informal learning, still, like, the model learns some structure and is going to have the same kind of shapes, because the shapes are about some more general math thing of representing things nicely in a space where you want similar things to have higher cosine similarity, because you are going to do things like dot product between case and values or whatever, and then you want them to have the same dot product in that direction or whatever, with some other vector.
Yeah.
Can we check the problem setup part, not the methodology part, so we can like speak more in a concrete way, and then we return back to this diagram?
Yes,
And
actually, I guess we can read first this figure and then go to the.
Start from the beginning, probably. Yeah.
Yeah. Okay. Let's kind of go a bit to the paper. Okay. So, Euclidean geometry. I'm curious. I'm not sure. I'm not sure I understand the reference to Euclidean geometry for activation space. Like,
maybe
okay,
for the shape it's making.
Yeah.
Yeah, like it's like, yeah, like when you just go into straight line, then you assume that the steering lives in a straight line, but it can be curved instead.
Yeah.
So
I
you
guess
get curved geometry instead.
Seems like so yeah, I can see how it's a curve here, but like, what is the geometry of the linear steering. It's just it's a direction. It's
That's
basically
Euclidean. Yeah.
a point. Well, or it's, I guess a line, right? You're assuming it's like a line.
Yeah. Just
Or
straight
like
line.
not a straight line. I guess the thing or
Or
yeah,
straight directions. Straight vector.
kind of feels like kind of fitting it weirdly with like the say that the steering vector is doing some the version is some space is just picking anyway. How do different geometries of activation modulate this behavior? We illustrate paths to activation space left is defined by different geometry. Interventions along paths in active space produce paths in behavior space. Makes sense. So yeah, it has division space. Yeah. Right geometry intervention follow a straight line. Such paths might cut across the activation manifold, ending on lateral behavior traces that pass of formation behavior space.
I wonder if like you know the diffusion meta model thing was kind of putting it back to this manifold essentially that they map here when you did steering, if you
Yeah, I
remember
guess
that
that
one.
makes sense. Yeah, I remember that one. Density geometry. Like, I can see, like, this example has thing, but I can't see how, like, if it's, you break things here, if you want to steer numbers with a line, like, those expectations of the week or whatever, right? With a simple, you know, linear steering, you have a thing that points here, and you, to move it through this, you try moving it in the opposite direction, and it kind of breaks, right? It might work
Yeah,
like the opposite is the opposite day, uh, although
like
not
yeah,
perfectly. If it's more something like 3D like this, it probably is,
like
but it's not. Yeah.
yeah, maybe they do it here as well, but like there was also the emotion vector paper from Anthropic, and someone did the same thing in parallel apparently. And like you also get this circle of like valence and effect
That
two
there is
dimensions, and
a
so someone steered it along this by 90 degrees. Yeah,
there is a thing here where you can have like you can approximate the curve more with more lines, right? Like instead of
oh, they
if you
fit a manifold. I see. That makes sense, fitting a manifold. That's more general.
like if you are trying to like you have a circle like this, you could just steer each day as a separate thing, right? Uh,
Yeah, they like
the reason
well,
is like
w-
the circle is going
like
to get
you
more
know,
features.
what what would that mean? Like you have Monday, so if you steer Monday, negative Monday, then you will have everything that's not Monday, and if you steer into
In
Monday,
this
then you
case,
will
if
have
you're
more
still
Monday.
negative Monday, but well, by break because you don't have the Monday direction, you have
Yeah,
complicated things with other stuff. But if you isolate the Monday direction on this thing, you're going to get in this example, you will get like Thursday.
because it's on the other side. Okay.
Yeah,
Oh, you mean
this is the
Monday,
same.
Tuesday,
If those happen
Thursday?
on the you know the manifold on the line breaks thing and those kind of thing. Uh,
Hmm.
Although that it's less because there are more dimensions, so you're only you're doing the line other dimension. It does some weird things where it's like seems like an artifact because it's less because it's not on the same direction. So the opposite is lower, but not zero effect. I mean, but yeah. Uh,
They fit an activation manifold to representations and a behavior manifold to output probability distributions. I really wonder how. Okay.
right. So geometry that fit the way this manifold. Yeah, more natural. Like they have a nice way of fitting the theme that works generally. That's nice. I don't think they do, but we'll see. Pulling what behavior space geometry into activation
Across
space, or at least
tasks and modalities.
unsupervised or something.
And also across tasks and modalities, so also in vision.
Conceptual space and model reasoning over.
Surprised.
Internal constraints of behavior.
They also try in-context learning tasks with more complex graph geometries. So they are looking also at more complex graph geometries, alright? In a video war model even, we use a task with a geometry corresponding to physical dynamics. Ooh. I wanted to see that, the features of physical dynamics in video models. Okay, that's pretty cool, if that's the case. Repr object for enabled principles of intervention.
I wonder if you can learn something by the if you take the diffusion model from that paper that we read and you correct the typical steering thing and you see how it changed it. If you can learn something about how the natural activations look like from that.
Like the diffusion model would show you the shape.
Yeah.
More. Maybe.
No, imagine doing Mech Interp on the diffusion model that is doing Mech Interp on the...
Yeah.
And then we use another model to figure out how that model works, and then we do steering on the steering on the steering.
Steeringception.
I
wonder to what degree that will become lossy. I believe.
I mean, it has to be because already the diffusion model is probably not that great.
Yeah. This is very cool paper. I think at least I'm still parsing the abstract, but like because I believe there is something like geometry of deception, for instance. That's like in some sense universal. So maybe this framework could be used. Did someone try to look at some like not just deception direction but deception shape?
Oh, the steering as a problem of geometry. Yeah. So steering can be defined as a problem of finding a geodesic connecting 2 points under different activation space metrics. Linear steering assumes a flat metric geometric. Steering along the activation may fall use a metric divided from natural activations. And stereo activations for. I think this is nice. I will. Obviously it's better if you can do that, but the thing I would worry about that is, can you in practice find all of the geometries in a nice way? Because so far it's mostly people finding a bunch of those in an ad hoc way, and it's not reassuring that, like, as the Luther people said, that is people kind of keep finding the same ones.
Maybe there will be some more automated, unsupervised way, like SAEs, but instead shape AEs.
I'm curious but I'm curious why they take off fitting the manifold, if it's related to that, or if it's something that could evolve.
Yeah.
Or if it's something where they.
Yeah. Okay. Now I was thinking, at which parts does this approach can be said as like, it might be applicable or maybe somewhat aligned to essays, like maybe in the compression part, I think.
SAEs disentangle the representations So I would assume you could find the shapes even simpler because your stuff isn't in this weird entangled superposition. Well, it still is. It is still polysemantic, but much less. It's more of monosemantic. I would assume it would be simpler.
Yeah, at least for
Oof.
this task, it seems monosemantic because it's simple, right? And when we move it to more complex tasks, that time I was thinking like, what might be the secret sauce?
Yeah. Like at least I think like for certain stuff, if you benchmark normal vector steering and SAE feature steering, you get better better results with SAE feature steering. So then you can potentially do geometry over SAE features, I would assume. Did someone try to do that?
Sorry, I was saying like I gotta go real quick and then come back after some time. Would that be fine?
Yeah, it's going.
Yeah, sure.
By the way, so I must say, I like so they did test. This is really interesting for the how automated can we make this thing. They did find first multidimensional graph structure learning context. I'm curious about that, and geometry of a physical position in the process that you already talk about.
Wow.
That's-
Okay. That's like place cells in the brain.
Yeah.
Similar. Not
I
same.
wonder if that's also some kind of circle or.
Hmm. Yeah. I posted into interesting findings, I think. Yeah. Neurogeometry of mice navigating a maze. It looks like a circle, as you can see
Oh
here.
no! Everything is circles. But that seems like if it's if it's just a circle, it's not a one. Isn't it a one-dimensional variable? Feels like it should be 2D for the maze or something, right? How do they? I'm confused how the maze represent like the full maze in a single circle. Uh, I
Yeah,
guess
I'm
it
not
could
sure.
be multiple
But there's a
circles.
whole video, big research on place cells, and Artem also has a video on this mice experiments, which is a computational scientist person on YouTube.
I guess
Mice.
I'll look into that. It might be just be multiple ones or just one.
Yeah, neural manifolds. I think this this video is I think on that paper, so that's more approachable maybe. Oh, no.
Okay.
Yeah. Okay. So like because this this all the good fire papers blew up, so people from all the other fields were also like posting, oh hey, Mech Interp is rediscovering neuroscience, and so it's funny.
I'm curious what.
Also
There's
go
a
ahead.
need to look more into Twitter about the response of the of all of the of that fire papers. See
Yeah,
that it's
like
interesting.
at,
I
at one point my feed was only responses to good fire papers when I scrolled it, nothing
I
else.
haven't looked at Twitter that much lately because my phone broke and I have to fix it. And it's
Oh,
fixed now, but I have less addiction to
less
Twitter on my
addiction.
computer, right? I just had the
Understandable.
habit of opening Twitter. At the moment it broke, I like it's just like I can look at Twitter on my computer, but it's not the same. So I and
Carefree
I
of the
probably get
shackles.
back to reading Twitter constantly soon anyway. But
Yeah, yeah. Also, like the ear is doing some Fourier transform stuff. Apparently, if one tweet I saw was on this information. But I think even eyes are doing something similar. I don't know. And yeah, so and like so people were pointing at like, oh my god, Transformers rediscovered Fourier transform. Well, the ears as well, also rediscovered Fourier transform.
yeah.
So yeah, I guess that's
I
another
mean, I
one.
think I think that we're seeing why that's the case. Like, it's kind of a general thing about trying to represent things in some volume with some, represent variables where you want. You basically want to represent a line or something like that, but you don't have a space to put it as a line, so you kind of curve it.
Yeah.
You don't even need the part where you're doing linear operations, but the brain might also be doing linear operations too, with no linearities in the middle. Like it seems. Well, I don't know that much, but I think that people do like a theory. That's not completely unreasonable. Is that the neurons might be, the all the synapses might just be doing basically a matrix multiplication with some
In the brain, you mean?
non-linearity after. Sorry, can you
Yeah, you
that?
mean in the brain?
Yeah, in the brain.
Yeah, there's a lot of complexity, but yeah, I don't know.
But like in the sense
The
that
differential
it's
equations
basically
behind.
the activations in the synapses get added, and then there's
Yeah, I
some
see.
non-linearity after.
Yeah, like as far as I know, like the differential equations for like specifying how the neurons compute in the brain are pretty insanely complex. The more deeper you go into them, apparently, all the different channels and all the electromagnetism, essentially.
I mean, I feel like if you
Yeah,
get into that level, you are also going to find that the equations for how a neural network works are super complicated because you need to do all the math of how the transistors of the GPU work
oh yeah,
and
that's
CUDA and whatever, right? I
yeah,
mean, maybe you're just
different
doing a
levels of
lot of
analysis.
complicated things to just run a matrix multiplication.
Mm.
uh,
I know there's like predictive coding and Bayesian brain, which looks at it through the lens of Bayesian statistics.
I feel like the predicting coding thing, stuff is kind of feels. I don't know that much about it. Feels like it seems pretty tautological in that there is some sense in you can see everything as predictive coding, so it doesn't not say much.
Well, it's as far as I understand, it's like a framework for theories, and then
Yeah.
people are trying to find exact like algorithmic implementations of these, which is extremely controversial apparently. So yeah,
Like you can see
and
any
it's hard to.
any optimization as prediction with some fancy prior, so it's kind of trivial in some sense, but
And
yeah.
some of it is not falsifiable, yeah. That's the
Anyway,
common critique of the
going
primitive
back
principle.
to the paper because yeah, I think we will be speaking an hour and people left and we have barely touched the paper. No, I feel bad in case people didn't, didn't get to wanted to read the paper and didn't get to see much of it, but we'll see.
uh,
I mean,
yeah, well, let's read. Okay, that goes blah 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 address. I really want to understand the mathematical formalism they're using there. So let's see. Yeah, like the Euclidean geometry makes sense. You just add vectors that are like straight, and like if you change your geometry to non-Euclidean, then you can add vectors that are not straight. So yeah.
conceptual spaces in cognitive science. It's patterns of inference. Because that is captured by a metric TC, measure the temporal distance between days.
Pass to the activation space.
Indeed, when the humans mistakenly report the current date, the most confuses with its memory days. Makes sense.
Flat geometry. Flat geometry is the same as Euclidean geometry. This is cool because, like, in general relativity, you need this map of curved spaces, and you also can use it here. I'm just happy that the same map can be used in different places like this. We'll see. And
distribution to the model on the tokens in the so they have activation space and behavior space.
density geometry. A density-based metric whose geodesics, that's from relativity. Well, it's from the math, but geodesics are used in relativity. Interesting geometry of.
Okay, so they are.
And geodesics are just paths on a curved manifold, basically, in a curved space.
Yeah. Also, I see that they are look at the behavioral manifold. They have already some like this is the kind of method. Is kind of like they have some question and they have some days of the week and they have some tokens that they are doing the behavioral thing over. And this is that's very. This is like it would be slightly annoying to do more generally, right?
Can you say it again?
So here they have when they talk about the behavioral manifold and all that stuff, they're basically, doing the
So that has to be constructed in supervised way, or
yeah.
so you have to.
I mean, you just need some metric, right? But here they doing probability over the. You could use some other metric. They are doing the probability of specific tokens, right? I wonder what they do for the position or whatever. Maybe they do fancier things. But yeah, this is in sense a supervised. This is a supervised kind of thing for the behavior. Then curious, they might not be a supervised kind of thing for the other, for the activation space. Maybe they find the shape there. But let's see. My guess is they are going to. I haven't gotten to that part yet, but my guess is they are going to find the structure on the activation space by doing something with the behavior space. But yeah. You could also do something where you take some points from prompts and you find the structure, but even then you will need to know what you are looking for. Like you need some series of questions. Huh.
Yeah. I mean, you could maybe SAEs could find something.
I feel like so the thing is with SAEs or any kind of method like that, you are only training them or doing stuff with one input at a time, right? And this kind of structure is the kind of thing that, I mean, they might still learn some unsupervised methods that is doing one input at a time. You're using gray instead to try to find it. But you could feel like you need some method where you take a bunch of activations on a series of questions and you find structure from that, but then you still need some series of questions that you think they are going to have whatever variable you care about, going to have different values. Maybe you can get still a bunch of variables for a bunch of different texts. But and it still feels like in some senses requires some reasoning about the text, about what the prompt is, and how, I don't know.
Like the fact that you still have to give it some training data to train the SAEs, you mean?
Yeah, but not exactly that. I guess you can still find some. Maybe you can find some supervised
like
way.
my like my idea was like on essays you can just train it on general data set, and you find a lot of unsupervised concepts in essays. So maybe you could somehow extend essays into something like like features on a shape like this, or something like that, and see if it just gets learned, and you in
Yeah.
unsupervised way find some
Like,
features corresponding to some
I guess
concepts
I imagine
rearranged
a
into
lot
the
of
shapes.
like imagine for example you have a lot of text, right? And some points like you have some random text and sometimes it talks about days of the week. So you are going to have examples with points here, points here, points here, points here, and so on, but not I don't know here or whatever. Like some not points, not exactly points because the actual activations are more complicated, but some direction of the activations is pointing consistently here and not here or whatever. And maybe you can find this circle somehow in an unsupervised way from a lot of different examples.
Oh, what about the scaled isometry part? Like, I think I missed that.
Hmm?
Didn't get
The
there yet.
yeah, you can see in the diagram, right? Like the scaled isometry.
I have no idea what that is. But
I mean,
let's see the figure.
just by looking at the shape, I think they are probably pointing to the direction of the sequential data they used, or I mean, whatever they used.
Okay, let me.
Well, isometry is like this distance preserving transformation between metric spaces. That's bijective. So you can rotate it, I think. For example, like reflection should work.
Oh, they are
Because
talking
the
about
distance
the
is the same.
symmetry between the activation and behavior space manifolds.
Oh yeah, so you have the same shapes, maybe just in different locations, basically. And you have this bijection that's preserving the distance
Okay,
between
so
the two
the
metric spaces.
uh,
A metric
so
space is like a set that has a notion of distance. So because you have a bijection, and you are preserving distances, I guess you can also make it smaller potentially.
so
And just
I'm not sure I
redefine the metric.
understand what the okay. So I
Mm.
understand. So the activation manifold. So the activation space is just the activation space, like the what the activations are, right?
Yeah, I will
Each
skip the
point.
text and just go to the math. Yeah. Where does the math start? Running example, concept geometry, notation. Okay, so activation space A is Rn. Okay, makes sense. And the bearer space is open probability simplex.
What's the open probability simplest exactly? Require open simple. Like on these shapes,
See.
what are the dimensions on the thing? Like I get is something about the probability of the different days of the week. But
Well, at least simplex you can see as a generalization of triangle, or like of point, of line segment, of triangle into arbitrary dimension of tetrahedron and so on. So that's a simplex. Open simplex. What is open
just to
simplex? Geometry. I guess open because you can open it, like you can have an open triangle. Algebraic topology and geometry. Ooh, okay. This is from algebraic geometry. Oh wow, they are using some nice math in there. I remember going through very basics of algebraic geometry. And I remember nothing. Just the simplex itself. Oh, okay. I think I found directly open probability simplex. Open probability simplex. Probability simplex. Probability. Is k-dimensional simplex whose vertices are the k plus standard unit vectors.
Fit in the manifolds.
Do they assume readers to know what is simplex and other things? I wonder if they're like if they have some explanation before.
Yeah, I see,
Or do they just assume that people
I still
know it?
don't completely understand what the activation. Well, maybe there's a fit in the manifolds here. Maybe there's the better space here. To fit the activation
They're using
manifold,
Heidegger space.
we reduce activation vectors to 64 dimensions via PCA. Okay, makes sense. Compute concept centroids and fit qubit splines through centroids. Aha.
They're using a lot of math terms that exist that I don't have memorized. So I think what should be done is take the math terms and just decompose them into the definitions.
Aha.
And that
You
will
can
make
ask
it.
Claude to do that.
Yeah, technically. And also ask, like, make it search web ideally with source. Yeah, that might be simple, fastest actually. Yeah. Like, there's like Heidegger space, for instance, is another math term. Like, centroid is a center of a shape. A geometric center.
I guess I can agree with. You can keep looking at that. I might keep looking at the rest of the paper for the like while you focus on the math part that we don't understand completely yet. I can look at the other stuff and see if there's other interesting things that are
Okay.
more. But anyway, so structural correspondence. So they have this. Yeah, they're talking a lot about. Yeah, I think we're going to have to understand what behavioral space is exactly, because there are a lot of the things they're doing is comparing it to activation space.
I wonder if it's like related to like, for instance, like if you have the emotion vectors and that forms a circle in the valence and effect dimensions, that's like the activation space, and in and like when humans are like
but
mapping it
how
as
do
well.
you get the? And it seems like here in behavior space they're talking about, probabilities of the output of the model. So, but okay, let's see what I asked Claude, and it says that. Okay, it's probability since the behavior space set of all valid probability distributions of the array categories, the 7 weights plus other. It points on the space full probability distribution, not single token, but space probability. Okay.
The exact definition.
Okay, so fair. Behavior space, I understand. Behavior space, so Claude is just the probability distribution over outputs. Although they, for example, on the days of the week sample, they restricted to the probability of the distribution over days of the week. I guess they just take the tokens, Tuesday, or maybe they are 2 tokens, but whatever, It's just they have some probability distribution and like that's the space, and the points are you make a prompt, you get some probability distribution, so you take the point, right? And from that, they somehow make a manifold. I'm going to get to that part. I'm assuming that's the thing they get into.
Oh, scaled isometry is the correspondence. That preserves the shapes and relative distances and their overall size by a constant scaling factor. Okay.
Okay, I think. Well, are they also just doing a PC? Wait. I think I might know. Let me fitted manifold. Map is centered to probability simple. Yeah, I don't know what to do, but
Vectors of strictly positive entries summing
okay. So
to 1.
I don't understand the heading space thing and all
Oh.
that, and you can look into that and explain it to me later. But from the impression I'm getting, this is just a way of doing something similar to doing the PCA and get. I'm curious why they don't just do the PCA over probability space, but that doesn't make sense. Like I guess probability space just each dimension is like each token is a dimension. Probably, yeah. So it's maybe you can just. I mean, it makes sense that if you do a PCA of that, you get a circle or something.
Let's see. Approximate isometry, so it's even approximate. That's nice. Okay.
Also, by the way, Claude says that the Heidegger thing is a way of mapping it into a sphere, into a unit sphere, like the probabilities.
Oh. Okay. Let me see.
Where the Euclidean distance on the sphere is this Heidegger distance, that is something about probability that is understand by probability nice probability distribution distancing. Okay, so they.
Where did they mention it again? I don't know how exactly it was spelled. Hey. My mind is constantly saying Heidegger, but that's not it's not Heidegger, goddammit.
Yeah.
Okay.
Heider, whatever, yeah. Hellinger, I think. Or whatever it's pronounced, but it's written Hellinger. Or at least it's written in the way where in Spanish I will pronounce in Hellinger.
Yeah.
Or
Hellinger distance
Hellinger distance.
between two distributions, where the norm is ordinary Euclidean and square wise.
Yeah, so they are doing this Hellinger thing to the probability distribution, and they are doing the just PCA on the other the activations, and their idea is that like the geometry you get is isomorphic. Like there is some structure to the outputs where Monday is closer to Tuesday or whatever, and that's related to the structure in the inputs. But I don't feel this feels like this doesn't work for the necessarily for less obvious things, like things that are not about the structure of the data directly, right? Like the line break thing.
What's your point again?
My point is this kind of method you couldn't use on the line break example.
And why again? Because it's too supervised.
Because you can't get there is no behavior space to get, or like behavior space is I don't know where you put the line break. Like they're talking about how the manifold in the structure is directly the same as the it's isometric or whatever.
Isometry.
Yeah, what was isometry exactly?
Isometry is a bijection between the two manifolds that's distance preserving, and it's also scaled. So you can scale it by a subconstant factor.
Okay.
And
So
it's
basically,
approximate,
the same
so
things
it's
that
not
are
one-to-one.
closer. Even if the shape is not the same, the same things that are closer are separate, right? So are the same distance. Things are the same distance, but with some scaling.
Yeah, the shapes look approximately the same.
The things are proportionally the same distance. It doesn't have to be the same shape, right? Like
Yeah, it's approximate.
No, but it could also be very different shape as long as the distance are the same, right?
Yeah, it's distance preserving. Yeah.
Yeah. So like, don't. For example, I don't know if you look at my screen. So this thing and this thing might have very similar, right? Like if you make
Yeah.
some, I mean, these are both the same. I think they're just two representations of the same. They're different views, but let's assume there were different objects. Let's say you have something flat like this and something like this. Like as long as
it's top view and side view. It's
yeah.
different views.
Yeah, I know, but even if they were different, imagine that they were different objects. I'm just using it as an example. They might still have they might be isometric, right? Because as long as the distance in the up direction is the same as the in this direction. So like, it's not about shape; it's about distance, which makes sense. But I think
and the manifold paths look the same on the middle.
Yeah, but I feel like this is a weird, like, this is not applicable to all behaviors and all things, and it's kind of not the exact thing to look for. How to explain it? So thinking about, imagine you can want to do this kind of analysis on the line break example. What do you do? Like, I don't know if you understand the thing they are doing yet, though. As I understand it, the thing they are doing here is just on.
I still don't get the behavior space. How do they get the shape?
So the shape is from applying the math that we don't completely understand yet, but to the probability distribution.
Applying the what?
The math. I mean.
Math. Okay.
Yeah,
applying the math.
Like they just do the same. They when they fit in the manifold thing, they do this. How to explain? So they do the Heidegger thing and map it to a Hellinger thing and map it to a sphere according to Claude, and like so when if you plot it in whatever way, you get a circle. If you plot the days of the, if you imagine you have some space, right? That is, each dimension is a probability of some token, right? The thing is, with prompts on this kind of question, and my problem with this that it's only on this kind of question, which let's do some things, but it's not a it's not a more generalizable thing. In this kind of question, you get some structure where when you ask what's 4 months after January, you are going to get probability on the current month, but also a bit of probability on the surrounding months, right? So there is some structure in the probability distributions over from different data points, right?
Okay, that makes sense. Yeah.
Where
that makes sense if you plot this.
the same things, and this is they do some math with the Heidegger thing, with the Hellinger thing that we don't completely understand yet, and that leads to that structure is plotted as a circle.
Yeah, if I see approximately what they might be doing now is like if you just imagine the probability distribution of the next days of a week, then it is circular by definition technically.
Yeah.
So like if it's Wednesday, then the previous ones and the later ones are like lower. So each day of a week always creates a peak. So that makes it Fourier-ish basically, and you get a
Yeah.
circle.
And they're just using some way of plotting probability distributions with a nice metric where the distance within them makes sense. Which is the Heridinger thing that I don't completely understand, but apparently, yeah. And then they get this shape, and they are just saying that the distance on the probability distribution under that metric is, has the same distance as the distance in activation space on the circles.
Yeah. I see. That's the approximate scaled isometry.
Yeah.
Yeah.
And I think the paper a lot of it is just and on the other the activation space just they just do PCA and then fit some do some curve fitting
Cubic
on it.
splines.
Yeah, I don't remember how curve splines work exactly, but it's this kind of simple curve fitting thing, right?
Yeah, splines are. There's
Or
also Bezier splines and
the thing
others.
where you put the point and then you the are pairwise primer or this kind of thing.
Yeah, like splines are like
The doing
defined
lines
piecewise by
between points.
polynomials.
Yeah. So they just do some curve fitting on the thing to make the curves to between the points to make the curves from doing PCAs on the centroids
Yeah,
of
that
the
makes
PCA.
sense.
So yeah.
Oh, that's a good way to create it. Yeah, that makes sense to me. Interesting.
But yeah, I want to the thing. This doesn't apply directly to the like. If you want to do it, there is no nice probability distribution. There are things that have this shape. I guess this kind of analysis is telling us something interesting, but you can't do it for other kinds of steering, right? Because, like for example, even if it's at the same kind of shape on the line break thing, there is no clean way of taking the probability distribution for the behavior space, right? Unless you want something like probability distribution of where to put the line break or something.
Yeah, maybe that could work.
And then you but like
Actually, maybe that
even
could work. Position of a line break.
but the thing
Apply
is
that.
that's only works because there is a direct relationship. Like imagine that you are doing some other math that has this kind of representation. Like the output distribution doesn't have to have the same doesn't have to have a linear relationship with the distance on the representation. If it's a representation that's not like it happens here
I think
to
I
be
see
the
what you mean.
case
Yeah.
that this directly that yes you have these days of the week thing and the prompt asks about the date of the week and you represent the date of the week in some specific direction. But if instead it was some math where there is some intermediate representation where you are using some number and then you multiply by the number and then you divide by the number, you do a bunch of operations and then on the end ends a completely different number, like the distance between the original numbers don't have to be the same as the output, the distance or whatever of the prompt. They will be the same if it was linear, but it's not.
Yeah, I see what you mean. Some stuff isn't represented in the output directly like this,
Let's
basically.
see if they say something about that. Anyway, so
Maybe in the
yeah,
limitations section, if there is any.
so apart from that, I guess we can. Yeah, we've been here more than 1 hour. Let's actually get a bit through. Okay, but I think I understand now what they are doing more or less on this plot, on these plots. If I will have to actually understand, what the Heidegger,
There is no,
is
yeah,
for this and some things.
and there
But
is no limitation sections. That makes me a bit skeptical. Okay, simplex.
Variety representation behavior by intervention. Okay. Oh, by the way, Hinton, I don't know how much you were paying attention now, but yeah, I think we figured out how these plots work and what the isometry is and all that. More or less. I can try it. Oh, if you're talking, I'm not hearing you, by the way. I see that you are muted, but yeah.
Where do they use the word probability simplex exactly? That's the behavior space. Ah, okay. Oh, okay, I see. Wait. Conceptual domain. So I'm now seeing the math of the each vertex. So the open probability simplex.
Oh, they're saying
Well,
that the circling behavior space and novel discovery.
like
Sharply
I
picked out
wonder how
proposition
it
predicting
connects
more
though.
maps on target concept. With the concept is neighbors. Yeah, I guess it could be more general if there's something. But I don't think the probability distributions have to always work the same. Uh, like it can be that there are similar concepts as there is some very sharp thing. I don't know.
Yeah, like probability simplex is basically just a simplex, which is a generalized shape, like generalized point, line, triangle, tetrahedron, and so on, into arbitrary dimensional shapes, where the different vertices just correspond to standard basis vectors.
Why it's that simple? Like why are you talking? Like when I imagine this as just a space with each dimension as a token. What's the difference between that and saying it's a simplex?
You you can map it to this geometric visualization.
Okay.
It's a mapping between the geometry and the vectors. Well, the probability space basically, the RK, where K is the dimension of the simplex, I think. Each vertex corresponds to the distribution outcome I with probability 1. Okay. Every other valid point probability distribution. Every other valid probability distribution is a convex combination of these vertices. Okay, so like those are the points which form the this is one probability of this exact thing, and you can just move between the points which are like interpolate between them, I think. Yeah, that makes sense. And they also have to sum to, because yeah, they have to sum to 1. Okay, so it's just like I see.
Okay, so they are saying here also that the casual intervention thing is that the hypothesis that if you do interventions by doing steering along the manifold, it should make the corresponding move in the output distribution, right?
If you do intervention by steering the manifold, you wait. Did you say that steering on one manifold should correspond to steering on the other manifold? That's what you
like
said.
one is one was the activations and the other is the output, and like I think that they said they're saying that these things are causally relevant. Like if you do a steering on along the activation manifold, it should change the the behavioral manifold correspondingly.
Yeah, that makes sense to me. That should be the case.
And that's the experiment they do later on section 3, basically.
Mm.
I think this only works in these
This-
examples, and there are other examples where it won't work because the relationship between the activation you are looking at and the output are not like directly related.
Oh, convex combination. Oh, convex hull.
In
So the
fact,
convex combination is a special case of linear combination. Okay. That respects the laws of probability.
Guys,
Weight
I gotta
average.
leave now. That's fine.
Okay, bye-bye.
Okay. See ya. Yeah, thanks for coming.
Yeah, thanks, man. Yep.
The division is my fault. Okay. Oh, we don't have. I wonder if I should. Later, we have some people that are not that many. I wonder if I should do, ask people when they want to do the papers and all that. Sorry,
you
when
mean
we change the reading group again, we'll see.
must be on a day where I'm not busy myself, ideally, or should be. Yeah.
Yeah. Can you come to the next one, by the way? If it's on Wednesday.
Next week, right?
Yes.
Not this week. Yeah. Okay. Yeah, I think I can move my work to.
Let's see. Like the
Yeah.
last time they just asked me for the when it was the reading group, I said M5CT, but I could change it, so we'll see what they say.
Mhm.
We're likely going to do that other paper that I.
Oh, you know why the simplex is denoted as the delta? Because delta looks like triangle and simplex is a generalization of triangle.
Uh,
That's genius, actually.
I'm confused why it's a triangle, but okay.
Well, it generalizes triangle technically, but it generalizes also
Let's say
lines and
you have
points and
like
squares.
if you have 3 tokens, is it a 3D? It's like a pyramid or like what?
You mean triangle in 3D?
Let's say you have on the probability on here. Let's say you have a probability distribution with 3 possible tokens. Is the idea that you represent it with a pyramid or something?
Well, that should be just a triangle because you have just 3 points.
Okay, so
You would need
you need.
4 points to make it.
So yes, you have a triangle and it. Oh, I guess it's a triangle because they have to add to 1, right?
Yes, that's just the probability simplex has to add to 1. No, not add to 1. Each point corresponds to a probability distribution where
But the reason
the whole thing is a
it's
probability distribution.
triangle, it's because it has to add to the probabilities have to add to 1, so you need to have a max like like if you look at my screen, I don't know if you can see my mouse. The reason to represent this as a triangle, right, instead of just saying a 3D thing, is that in this way, like you can't have points here because the probabilities have to add up.
Yeah. And you can interpolate between the all points. So every
Yeah.
point in the middle is some convex combination, which means a linear combination that respects the laws of probability, basically.
Okay, yeah, makes sense. Like I was
Of
just
the 3
confused because
points.
if I was thinking of probability space as a, some thing with, for example, if there were two tokens, two axes, and one is the probability of one and the other is probability of the other. But if you represent it like there are points that are not valid, that don't follow the probability distribution, right? Like if you have some, like if this graph was the probability of two possible things, things here wouldn't make sense, for example. Or here will also don't make sense because they don't add to one. It has to be some, it's a kind of some other shape. And you can instead do a triangle. Let's see that.
Yeah, this probability simplices seem to be like generally try to formalize this idea that any like when you have like n amounts of points and all of the each point basically corresponds to a single outcome with one probability and the other outcomes with zero probability, and the fact that you can also interpolate between them basically, and when you get different shapes, that means you have different dimension, like different possible outcomes the more points you have.
Okay, so they do steering, by the way, and they
Linear manifold steering.
only
How
the
do they do that?
corresponding with
Interpolation between. So you either just do the linear one. Wait, so they remove part of the age parameterization. Okay, so simple. I'm now going through the notation. So Z is the cardinality. Okay, that makes sense of the conceptual domain. So for weekdays, it's 7 and other. How many outcomes coordinates the simplex is over? Be a single point of the simplex.
Yeah.
Also, the simplexes are like idealized versions, and in practice, it's this approximate, apparent or not. Well, no, not really.
No, I mean the simplest is the possible space, right? It's just that the it's the space of possible probabilities. It's just that you are picking points in that space and then you are trying to find the structure in those, and that's how you get the circles.
Yeah. Yeah. The triangles can be arbitrarily sized.
Okay.
But they have to respect
Small
law of
order
probability.
behavior transition. Also, yeah, here they're basically saying about how if you steer through the manifold, it produces a smooth transitions where you slightly change the activation and slightly change the probability from, I don't know, Monday to Tuesday. And instead with steering, you don't do that. It's kind of breaks and you maybe go to from Monday to Friday or whatever. And that's just
That makes sense, yeah.
yeah. I feel like a lot of this is they kind of pick some problems where they found that it has this structure. It's not necessarily the case for other kinds of problems that have different structures.
Yeah, definitely. Like, if you have a general shape that you can fit, and if you have onto a general manifold, then you can potentially steer arbitrarily shaped structures.
Arbitrary shape structure can be arbitrarily complicated and hard to find.
Yeah, that's true.
Like the nice way we have of fitting arbitrarily complicated shapes is machine learning.
Yeah, that's one way to say it.
And then we don't know what the shapes are.
Yeah. Now we're trying to find some interpretable shapes, at least, in the insane space of possible shapes. Low energy. They're using the
Why
word
is
low
low
energy
energy?
region. The model
What's no?
unintervened forward passes.
I'm going to ask Claude to explain it in other
I
way.
don't know.
Uh,
Energy functions. Is it like probably okay? So like, they're citing Hopfield and LeCun, so it's related to the more like the physics kind of energy and not energy-based models. But I still don't.
Closest
Where like the
low energy
it's
is more
low to
likely
minimal.
and high energy is less likely.
Okay.
And
Yeah. Okay. So it's energy related to no. I'm not sure if Claude is correct actually because wait.
it's looking as energy here as the
Energy. It's in the
logarithmic of
paper.
no.
Yeah, you see in the go on top. Go on top. Right. Yeah, here.
Yeah.
Energy corresponds approximately to minus logarithm probability.
Yeah, so this is just saying that a high probability isn't it just a fancy way of saying a high probability part of this space?
Yeah. Well, it's like. Oh yeah. Because it's always under 1, then it's always negative, therefore it's always positive. It shapes the probability a bit. So like if the probability is extremely low, then you have very high energy. If the probability is 1, then the energy is 0. Yeah, high values for unlikely ones, low values for likely ones. So it's like scaled by logarithm as well. So basically 0 probability is infinity energy and 1 probability
So
is
it's
0
just a
energy.
fancy way of plotting in a logarithmic way with the probability, but inverse. Like inverse
Yeah,
of the probability. Okay, yeah.
basically.
But in a way that sounds like it's fancy and about physics or something. And maybe there is some physics math
Well,
that people made for some math that people made for physics that makes sense here.
I think it's since there's logarithm, I think it has connection to entropy as well. I'm not sure how
Entropy
useful
is
though.
also about probability, like the logarithm of probability.
Yeah, it's yeah, basically.
The model probability distribution on intervene
Like
forward passes.
the issue I have with the word energy that it's used like billions in different meanings.
Kind of like
That's
in
another one.
there is something a bit similar in entropy, but actually I think it just turns out the physics entropy is just the same as the probability entropy.
There's a mathematical correspondence between the information theoretic Shannon entropy and the thermodynamic Boltzmann entropy. Yeah.
In that case, but I don't know if there is a relationship here between energy and the physics energy. Like, is the physics energy also secretly about high probability? That sounds like the kind of thing that might be true, but I'm not sure.
It is actually, I just realized. Ooh, that's maybe the connection because everything. Okay, I'm not sure if that's related to it, but like if you have a closed system, then the most probable states are like highest entropy states.
Yeah, but no, but that's not
because
the
second law of
entropy. Yeah, but I mean
thermodynamics.
about energy.
Yes, and you have low energy in high entropy states. So
So it's energy. Feels like there is something more that's not energy is just the inverse of entropy, right? Or is that just the case? I don't know. I need to learn more physics. But
I'm a
let's
bit
go back to the
confused
paper.
about because in physics energy is like kinetic minus potential energy, and energy is conserved in a closed system, so the energy doesn't change. But the way how machine learning people use the word energy is different than this. And it's more related to entropy. Like the higher the entropy, the higher the energy. Since it's less probable, or I mean, if you have a probability distribution that has higher entropy, then the different parts of the distribution are like lower probability. Therefore, it's higher energy.
But well, anyway, in any case, going back to the paper. So yeah, so they do steering, and they find that the activations steering works. Like it makes it makes sense as if you do a steering along this direction, it gets you the correct result. And there is also this pullback thing, reverse direction, which I'm curious how they do. They start with paths along the behavior manifold and optimize for corresponding pairs in activation space. Okay, so when you do probability here and try to optimize for paths that will change the probability to say a different month, that also moves through probability, also moves through the activation manifold in the same way, which is nice. It's a nice result, and I feel like you could use this to find. There is two ways of finding shapes here. You can take activations and find point, like doing PCA or whatever, but it's going to be hard. But it could be interesting if you want. There are most cases where it's better to do this kind of optimization. You have some behavior, and you do optimization with this manifold thing. Like you can do. Yeah, I guess you can train with the pullback thing. You could train probes. With
Integral.
you have some. You can get. You need
Cumulative output
some
energy.
output space that you don't necessarily have that in a nice way. Like if you're stealing something qualitative that you just see from problems, unless you have, I don't know, some other model scoring, and then you use the model to get the probability distribution of that, and try to steal from that. That has problems. But
You mean scoring how well the steering is correct, or how much the steering is correct?
if you here, okay, so here they are going from behavior to activation, right? So they get the same shape when they try to optimize from different some way of
By optimize, what is meant? Some training.
set of activations. Yeah, they set activations that yield the path of M to an activation. Actually, specifically, they probably explain it along here.
There's a Bachwiayata distance word, which I don't know what it is. Distance. There's so much jargon.
Okay.
Euclidean distance, so many distances. Yeah.
Okay, so they use this method.
Butterfly distance. What is that? In
For
statistics.
a path
Notion of
integration
similarity
space.
between two probability solutions. Okay. Another one then.
They use a lot of math on this paper.
I like that, but I have to just spend a lot of time just going through the definitions.
Yeah, maybe
if
for
it's
this
the
kind of paper
domain I
we should
didn't
have
look into.
read it beforehand instead of trying to figure this out. I mean, I don't mind, but I feel like a lot of other people left, and I worry that maybe it's just you and me that are willing to spend so much time on this here. At the same time, other people
At least
could
you
also
actually
just
understand it.
could also
compared
come
to all
having
the whole
read the
Twitter.
paper and actually understand them before and explain it to us instead. But people don't do that. But I don't know.
Yeah.
I mean, to be fair, today Hindle did read it beforehand, but I think he also just was confused by all the jargon and didn't actually understand everything on the all the
Yes.
stuff. I mean,
Like the
I could also have picked the
isometry.
blobs that were simpler, but that seems they seem less interesting precisely because of that.
Yeah. I wanna see how it's actually computed.
I feel like the blobs, a lot of them were just they just serve as a popularization of things that people have already found on through Mech Interp papers on all of this stuff. It's already well
Yeah.
known.
Ah. Okay, ambient means that, okay. I like this. This is exactly the kind of paper I actually was looking for. Mathematization of steering using manifolds and stuff like. So I really wanna just. This is a paper I really wanna understand in as much detail as possible,
Okay, so
including all
that
the
is a
math.
thing that maybe, but in a more general thing apart from getting to math, I think this is nice. So here the special thing. So they have three methods. There's three methods that they compare. So there is manifold steering, which is sorry, there's linear steering, which is the normal one. There is
Oh,
manifold steering, which you take a bunch of activations and you get the manifold from them. The thing is, you for this is kind of a thing where you need a bunch of examples that follow from the. It's kind of normal. I mean, it's normal since you also know, right? You have a bunch of examples, and you do PCA on the activations and try to find some structure there, right? And then there is the which you're only kind of all this kind of only works on curves the way they did it, if I understand correctly, because if they were just doing PCA and then they doing the spline curve fitting thing, right? And then there is pull bucket steering, which is cool. Which is the pull bucket steering is they take the output and they trying to find some activations that will move through the output
wait.
manifold. But this
I think
this only works if you have an output manifold.
Wait. Let me quickly check something. Pullback, pre-comp fiber product. I think pullback. I know that from category theory, and I wonder if it's related. Pullback consists of two morphisms: P, Y, G, P, G, F. You change, so you change it. Yeah, I think pullback is actually it has a generalization in category theory. I think. Actually, I'm not sure if it's this kind of pullback, because pullback is a word that's used in. It's again thing that has. It's like kernel. Kernel also has
Claude
multiple
says that
meanings.
that term here it comes from differential geometry.
Yeah.
That is like if you have a map from one space to another, you can is doing the opposite of from the target space to the from the source space.
Yeah, it's in differential geometry. and then that itself is generalized into category theory, which is where I actually heard pullback the first time.
The situation is okay. So how is it done in practice? So they have a behavior. So they have a path along
But
the
it's
output
useless, the category
space.
theory one. Okay.
So they have a
Well, it's
path
maybe not.
along the I don't know along the output space, and they also
Also, they have a Riemannian metric there, I see, which is also from its use in general relativity in differential geometry, I think.
okay.
Riemann metric.
So I think this kind of makes sense.
Smooth
So the
manifold.
Claude explains the pullback as this, by the way, which
Yeah, it's in
I think
differential
fits with
geometry.
my understanding. I just posted on the send it to you.
Or specifically, general relativity uses pseudo-Riemann manifolds, which is generalization of Riemann manifolds.
I think this kind of thing is nice. I don't completely understand how like that's how it works, but it's nice. But it feels like it's again the kind of thing that only works here because they pick a specific problem where the output distribution happens to have that structure, and that corresponds to the activation function layer. And
Yeah, that's likely.
and it doesn't. You don't. I guess maybe you can do other kinds of geometry, other kinds of things, but it still feels like there is no nice general method for this geometry thing.
Yeah.
Like, and I understand they're using, they're also using the spline thing there. So like, still assuming a certain simple shape of the. I mean, you
Yeah,
can
it
do
is still
a lot more
approximating.
points and approximate it arbitrarily or whatever, but yeah, it's still.
Yeah. Line fitting. Yeah. Subscript corresponds restricts every component to be strictly positive.
Oh, nice. They talk about so they talk about factor control in multidimensional spaces. So yeah, so there's things that are not just lines. Oh hi.
Hello.
Hello. Fight of file. Hello.
So we were going to this manifold steering paper from Goodfire, and so far we understood that like it has a lot of math and that we're getting through. But so far we understood that so it basically so they have the typical structures that we have people already know out on the model on the activation space with the models, whether there's a circle or whatever, and but they have a thing where they talk about also structuring the outputs that there are on these examples, where they, for example, ask the model what is 4 months after January, where that asking that activates the correct month, but also a bit the months surrounding it. So they do a bunch of math and they get another circle for like the output space, like in probabilities of different tokens of like different days of the week, for example, in this thing. And they show that the distance in output space corresponds to distance on like the activation space. And a lot of there is a bunch of plots on the part we got so far, which are just comparing output space with like the probability space and like the activations. And then they do some steering and show that you can do a steering and it works better than on the it has more smooth transitions of probability between different days of the month. That if you just do linear steering, if you move along this curve shape, which makes sense. And yeah, that's mostly what we gotten so far. And they did do this pullback steering thing that I don't completely understand, but it's something about they go from behavior and find the changing activations that will change the behavior a bit on the behavior circle or whatever. Like on the output circle, if you change slightly on one mode to another, then you get the same kind of shape on the activations.
Yep.
And that's the where I was. And now apparently they're talking about between that there is also a lot of details with a lot of math that we don't completely understand. But Burn is getting to that. I was reading the next part.
Yeah, I'm basically searching all the jargon.
Yeah,
it is
no,
stuff
this
from
I'm going to have
differential
to-
geometry. Oh, go ahead.
I'm going to have to. Sorry. I'm going to have
Continue.
to be very specific. I mean, I'll have to read this paper very, very closely.
Yeah.
Yeah, because this work is pretty close to what I mean, like what I'm actually doing research on, which I don't know. It's a bit cool and a bit sad, I guess. Cool in the sense of it's cool that there is a company that is taking a lot of this geometry stuff as far as they can. Like they seem to be really, really manifold pilled compared to like a lot of other
Yes.
groups. But also, it's very I guess it'll be hard to make a lot of contributions to this field if they're going so hard on it.
I think there's probably still a lot of stuff. And there is a lot of things to look into. We still don't understand most of the geometry of the LLMs anyway. Even this paper is a lot of the samples are the same samples that everyone uses with the days of the month. Whatever, so.
Yeah, the examples here are the simplest ones. The simplest shapes. They don't have more complex
I think
shapes
it's
in there.
because they did have some more complicated things later.
Oh yeah, at the end. Yeah, that's true.
I was going to go look at that now.
I wanna see geometry, I wanna see this framework applied to the line breaking circuit.
The thing, something I said earlier is that at least on this kind of structure, this kind of thing only makes sense because here they are asking a question where, like what is 4 months after January, and they are getting to represent it on the month, which is directly, correlated to the output. If this representation says Thursday or whatever, the output is going to be Thursday. But this kind of thing doesn't make sense on more complicated circuits where you find some intermediate activation that does something else. Like you get the length of the sentence on the line break position, and that's also this kind of shape, but it's not like where the output is something like probability distribution of where the line break is on something. And that's takes more than one variable, so there is no nice relationship on this. I feel like this paper is about some very specific simple examples.
Yeah.
You
only
works on that.
I think.
Well, they've been working on the same simple. Sorry.
I think you can just drop the behavior space and just look at the activation space and do manifold geometries there. Would you say phytophile?
Oh, I was just gonna say, well, these are like the standard examples I feel like for mostly everything. Other than I think there is something in this paper about this grid one, right? About the video LF. That one.
Yeah, that's cool. I want to look at that one. I haven't looked at it yet.
I think you can use the behavior space when you see a correspondence, but you don't have to use it. You can just do the activation manifolds.
Yeah,
manifolds
that makes sense.
Steering.
But they don't have I guess how they found. I feel like there is still no nice way of finding. There's no nice automated way of finding a structure in general. It's still for the other samples they just did a PCA, and then fit some spline curves to the points after onto the centers of the PCA. So I mean that probably was for simple things, but it's not. Anyway, let's.
Like you could do brute force, but that's computational intractable. Yeah.
5 manifolds, and so there is two-dimensional restricted coordinate system of the manifold, where steering along its coordinate controls an independent dimension of the conceptual space. Okay, so that's nice. So so this typical thing, there is some graph. Also, wait, which paper is this? Because it's maybe I also did some
I
research
don't
on the. Let me. I'm just curious because I did some research on this, and I think I might know on the graph stuff. I might know which paper.
But I like this paper because I was spending, I don't know, a few days just talking to all sorts of rationalists from Lazurong, and most of the time I just somehow in conversations converge that my dream is to have something like mathematical formalism for the geometry of all the different shapes, including possibly deception if it also has some shape. So this paper is basically doing exactly that. So I'm like, oh, okay, nice. That's cool.
I feel like it's just doesn't really have for generalized shapes. It just has some examples where they. But I'm curious.
Well,
let's first see what they do for the
like
this one.
I think it is you creating a general framework where like you have all these tools from differential geometry and so on, and like spline fitting and so on that you can use to essentially construct any manifolds. But yeah, the issue is that
Does
you
that
have
actually work? Like the doing a spline fitting for? I mean, I say spline fitting maybe probably generalized within of brute force. I don't know, but like, I don't. That doesn't feel like.
it's. I think it's it just splines are made of polynomials, so it's just like approximating the shape like using polynomials. Like, but the more samples you have, the better shape you can create, basically.
I guess you could generalize that, yeah, but
yeah.
that's assuming it's kind of a line. But I'm curious for this example because here in the space thing is a 2D thing, so I wonder if how they deal with that.
But I'm definitely biased towards. I don't know why my brain just loves formalizing. It's just I don't know. It's just a nerd sniper or something. Like I was trying to do the vector steering, and I spent like one day only formalizing vector steering in math because I can, and it's not really worth it. But now I have 2 pages of formalized vector steering, and I'm happy, even though it's useless,
things
probably.
like people were arguing on Twitter today about whether we need like better general theories of AI safety or whatever versus more empirical stuff like this, whatever. Random walks
I think
over.
both. Yeah.
And like how a lot of the theoretical stuff in Les Brown kind of died in the late last few years. And you don't see as
Oh
many
yeah.
people talking about the logical induction or whatever.
Yeah, I think I think I know the exact thread that I just read today. That
Yeah.
you read. Yeah, that's the thread I also read today. Yeah. Yeah, that's interesting point. I think it
I
started
feel like
with Anthropic being the biggest outcome of EA.
maybe
The thread.
you like I feel like maybe that's that's the kind of thing you like with the the kind of thing that Paul Cristiano was doing, although he's not doing that anymore. With like formalizing logical induction or whatever.
Wasn't that Ryan Glindblad or someone else
And
instead?
it's a bunch of
Yeah,
people,
but
yeah.
okay. Yeah, like I look at the logical. No, it's Scott Garambard. Okay, I look at the paper, but I didn't read it. But it sounds ultra cool. Yeah. Also, it's
I
very like
remember-
GoFi built, and nowadays GoFi, well, everything is neural network,
Yeah.
so no more
There
GoFi.
was also like Paul Cristiano trying to remember that he had a prize or something for the solutions to a math problem of like formalizing a thing of like heuristic arguments or something.
Like,
Uh,
yeah, like the issue is like with the formalizations you can make. So like you can formalize things, but then like if it's useful, like can you actually derive some useful theorems with useful practical applications from the
Anyway,
formalism?
going back to
That's
the
not the
actual
question.
paper, sorry.
Yeah.
So yeah,
That is
so,
great.
yeah, so they have this graph, and this is the position in some graph, which is nice. And
Manifold fitting.
also, yeah, this is an example of something that finally is not actually a circle, is some other structure which is two-dimensional instead of one-dimensional. I mean circle, but it's actually curves more generally, that one-dimensional variables tend to become curves. I guess this becomes some
It
kind of
becomes a
surface
3D
thing.
manifold.
Yeah,
Nice. Topologically, they also put in topology. Two-dimensional shape with surface with no holes or tears. Great. Let's put in topology. Let's put in all the math because we can. Is there a mention of category theory at this point?
no, you need to write your own paper for that.
Wait. Geometry of categorical and hierarchical concepts in language models is cited. What do they mean by categorical and hierarchical
I don't think
concepts?
that's just the normal meaning of categorical, not the category theory meaning.
As polytopes in the presentation spaces. Never mind. So next step is formalizing this manifold geometry in the category of manifolds of topological spaces, which will be completely useless, but it's great intellectual crack. But yeah.
Okay, try tokens assigned. Let Claude do that when you get next
Yeah.
to Claude 6 whatever, and they you can tell them formalize this and it does.
Yeah.
I just produce a lot of tests that you are not sure if it's correct or not, but it sounds very nice.
Yeah.
Oops, I accidentally.
Oh, hello, Rambert. We're going through the. Well, I'm trying to go through all the different or do you wanna summarize the paper for Rambert?
Yeah, if he wants to, I can try to explain it. I don't know.
You could just do it later, I guess.
Okay. It's yeah.
Well, Victor is now going through empirical results, and I'm now deciphering all the mathematical jargon.
I woke up late because I was doing the pivotal lap. I did that earlier yesterday. I was kind of tired today.
Nice.
Nice.
Yeah. So anyway, I'm curious about how the 2D things work, and I should actually read it. Because I'm getting started with the formalizing stuff. The show is the statistical pattern in random world tokens. Introduce a reconciliation of the graph structures. Okay, that makes sense. Like they have random walks through some graph, and that makes a nice structure because there are points that are closer, and the kind of thing that we had already talked about, where there is a general fact about if a model wants to represent some points where closer points are closer and separate closer points are more separate, there is some nice geometric structures to do that.
It's so fascinating in the first place that all these geometric structures, you can find them inside these models. What the hell? Okay, that was just a quick insight, or not insight, just realization. I don't know. Yeah.
This turn the language model to manage token distribution to predate token suggests the correct location with the random work on the grid. For 2 experiments, we assign arbitrary tokens to create and train the graph structures.
Copy.
Wait.
Okay. Z is a cardinality. Conceptual domain.
Okay, so the distance on the graph. I think it would be nicer if they have some example that wasn't from another paper, where they just just look at some thing that a model does
Well,
that seems like it
I
should
think-
have some
yeah.
structure, and you just
Like
check.
it seems to me like if you want that, like the first thing, I don't think I've seen anyone. I think the steering is new though. Oh, I see what you mean. Yeah. I haven't. I don't know. Like Goodfire found like some biomarker of Alzheimer in some protein or not sure what kind of model. So some biomodel. So that's a new Mech Interp result from them. So if you want specific Mech Interp results, then I am aware of probably just that.
Yeah, but I'm curious about ones that they can they find more by this kind of methodology of fitting splines or whatever, or they are just
Okay, I see.
only doesn't only work because they already know these examples have the have some structure like that. Yeah, so here
Like
okay,
this,
for
this seems to, or like I try to explain to answer the question. Like as far as I know here, like you do the normal finding of the shape like you usually do. You just put the PCA on the stuff where you assume a shape will be, and then all of the manifold stuff is just like on building on top of that. So yeah,
like for example, here they fit a 2-dimensional sheets. Do basically cubic they say cubic splanes but 2D basically, right? And
to the analog
this
of
only
cubic
you only
splines.
know to do
Ooh.
that because you're already expecting this to be a 2D representation, right? It's kind
Yeah,
of
like
very
Yeah.
kind of you already know what you are looking for.
well, I think what's new here is if you create this manifold, then you can do this manifold steering. If you don't create
Oh yeah,
this
I do
manifold,
think that's nice.
then you cannot do the manifold steering this way. Maybe I'm not sure what they did in one of the papers where they also found the emotions in the circle where they did a rotation 90 degrees, which steered the emotion accordingly on the effect and valence axis. So that's a similar kind of steering to this one, which is not straight steering, but it's like in a circle steering, literally. But this seems more general than that. If it's true they just steered in like 90 degrees, then that's a very specific type of steering. This is steering on an arbitrary manifold which can have arbitrary shape, which you construct by this spline fitting of all the different points that you have to create a shape, basically.
Yeah. Look, you're still trying to you're still making some assumption about like the dimensions of the shape or whatever, right? About whether it's like here it's a 2D like 2D surface and the other case is a line, and it could be
Like,
some
yeah.
complicated thing. Like the
It's
philokinetic 3 is
yeah.
probably something else. It's not like it's not exactly a
It's
line or
fitting. Yeah.
But maybe they
It's
have another
basically
example that is
fitting.
not. I think there was some another example. I'm curious about that. But okay, yeah. So and like if you try to do arbitrary dimensions curve fitting, you're just doing machine learning again, and then you can't interpret it.
Yeah, like this is interpretable curve fitting, I guess. You take those interpretable
old-fashioned
dimensions
curve
from the
fitting.
model. Well, yeah.
In this case, we use activations corresponding to the last token in context and compute centers towards location. Yeah. So and then
Well,
this
here you yeah. Here do curve fitting in like 1 or 2, 3 dimensions, while machine learning does curve fitting in like billions of dimensions. I don't know.
It's
Yeah.
nice that the steering also there's the same kind of relationship where the probability also is related to the adjacent shapes, right? The adjacent
Yeah.
squares. It's interesting is like this and not in diagonal, but I'm guessing the graph doesn't have diagonal connections.
This is so cool. Also, what is the example exactly? What does it correspond to?
So they have a graph, right? Like this.
Film, Fall, Joy, Back, Rain. Okay, completely random words. What?
It's,
No, wait, it's not
ignore
random.
the words. It's a graph, right? Like it's a
Context.
graph, and the words are just labels. They could be numbers, right?
Okay. So it's
Like,
just a graph, alright.
it's just a
Random
graph.
walk on a graph. Alright.
And you put random trajectories on the graph, right?
Okay.
And the model learns the graph structure.
So you do arbitrarily random walks over
Yes.
this
And
grid.
since salt always shows up after film and so on, right?
Wait, so it's not arbitrarily random. Oh, I see. It's arbitrarily random in the sense you only go to the neighborhoods.
It's arbitrarily random, but it's through the graph. Like there is no arbitrary connection, right? Film is only connected to hint and to salt. So salt and hint can only come after from joy or
so,
they can only come from the adjacent ones.
And from Jura you can go to hint, salt, mind, or back.
Yes.
Okay, makes sense. It's just a random walk,
So,
right?
so
you do
train
this.
the model random works, and the model learns the structure in that there is some representation of the model of this structure where in activation space the representation for film is closer to salt and hint than to rain, for example, right? And it actually has the structure of the graph in that you can fit a 2D curve, the manifold curve thing to it and get.
You basically get the graph.
Yes, you basically get the graph, and it gets this thing. Yeah.
And each point corresponds to the different
to one
points of the
position
graph.
on the graph, yeah.
Okay. And you can do manifold steering on this. Wait, so it's 3D, so you can also go inside? Or wait, how is it 3D? That's like the different combinations?
I mean, it's 3D on activation space, I guess. But it's a...
The graph is 2D.
Yes.
Or is it 3D?
The graph is 2D.
And why is the activation space manifold 3D?
No, it's 2D, but it's wrapped in a weird shape.
Wait, okay. I think. All right, because okay, so if you go to then.
Like if you on the other samples, like days of the week are in some sense they are 1D, right? They are curved because of because they are inside. They have to be curved inside the model. And it's the same shape that you have.
Like the issue here I have is that, like, I don't know if you have. Can you go from then to rain, for example? Like, can you also does it wrap around? Because
probably it seems like it probably wraps around because
I think it. Yeah. I think it has to wrap around for this to work.
This one implies it wraps around.
Yeah. So okay. Yeah, that makes sense then. So each state corresponds. And why is there more? Like there's like 5 while the graph has 3. I guess
this is
because
just an example. It's probably just you can do whatever.
Yeah, the graph can be bigger, so it's probably bigger, and you can just wrap around it. This is very cool that this works. Okay, and you can just do the random walk in the neural network instead of the original data.
Yeah, they're doing a steering by I guess it changes the output to like steering a fish if you were in some specific position. Like it, I guess, like these shapes tells me that this representation represents where you are currently on the thing. Like it's the last word, and it, and the output is the always on the surrounding things. So if you do a steering, you are basically you put on some position, and it increases the probability of the adjacent things. So it's basically just putting on the right place.
Wait, so what's the difference between the top and the bottom? It's the same thing, just from different different examples, maybe.
I'm not sure.
From different.
Probably
It looks like it's the exactly the same. It's just different examples and different perspective. Also, what is the black line
no,
on
it's
the
different steering
manifold?
paths. There are two steering paths. There's steering from.
Oh, right.
Yeah, from 0.3
The black
to.
is the steering on the manifold.
Okay.
The black line.
So
Do
here
you see
they're
it on
going
the black
from
line?
0.3 to 4.3.
Oh, I
So
see.
so they are doing from here to they're just moving it down basically. So
Oh, and they have linear comparing with manifold, and the manifold works much better. The manifold is steering down, and it seems coherent, while the linear just breaks down. It kind of works, but it's broken.
yeah, like the linear is on this here, and then still here, and then the liner makes the thing that makes sense that it's like swapping, like when it's backwards, it's point to the opposite one, right? Because it's wrap out.
Right, it's linear because you just go straight line from the start to end, right?
Yeah, like
so you go from direction
through the shape, so it's
yeah.
does this on the natural on the you go through things. For the UU liner is the same kind of the like on the numbers thing you go only through to the opposite number, and on the middle is kind of broken.
You can see the middle of the bottom one. That's it's like superposition of two possible, spaces. The middle one of the line here.
Yeah, we're confused.
That's broken.
It doesn't necessarily. It doesn't seem like it's actually wraps around. We're just confused by the broken liner ones.
Oh yeah, it doesn't have to wrap around.
Yeah,
but I think it's possible to wrap it around on the manifold because the manifold is wrapped around. Is it not?
Yeah.
Or maybe it's not actually. Maybe it's actually not wrapped around actually. Like, yeah, maybe it's not.
I think it's maybe I don't know if it's kind of hard to see here. But it might not
Yeah.
be that it's kind of wrapped around, but it's open on this side.
It might be like if it would be sphere, it would be cut in half.
Yeah.
Okay, that makes sense actually. Okay, that makes more sense now. I mean, you could wrap it around and you would get a circle, I think, and now you just get a line, 3D line.
Yeah, but that will be a different. I think you will get the kind of representation if you train the model with a graph where this film is connected to joy, right?
Yes. But then it would wrap around, yeah.
But it makes sense. Like the model has to have some void space here, so it doesn't. When you look at, so that the joy is separated from film, and so when
But this is cool because, well, I think one of the reasons why this paper seems so cool to me, like there's the whole the manifold hypothesis, and like that you can learn the data into low dimensional manifolds. This is basically confirming the hypothesis to some degree.
I mean, those models learn some low dimensional manifolds of data, but yeah.
Yes. And this just shows that on this low dimensional manifold you can find it sometimes if you know how, and you can steer on it, you can interpolate on it. Like the thing is, like there's this giant debate in interpolation and extrapolation, and people are like, actually we have to define extrapolation and interpolation using manifolds And if you do this interpolation on the manifold, that's interpolation. And actually extrapolation would be going outside the manifold into some coherent other manifold or something like that. That's some people are arguing that.
Take on that is that the whole debate is bullshit and is like not actually makes sense as math. Like it's like people are taking very vaguely our interpolation, extrapolation, but you rarely see them actually do the thing you're talking about of actually talking about some specific. We are talking about points in activation space or something. They are. I even there was a post by someone recently talking about this, and I feel like people are just kind of using it as a metaphor for discovering new things and saying something about LLMs are bad at inventing new science or whatever, and then saying if it has something to do with like it has something to do with extrapolation in the typical sense of the word of right, but it's not. I feel like it's very vague, and people that haven't done very good job doing an actual mathy thing where they correlate that to saying something specific about points in some space. They are not even like people talk about. They don't care they talk about the data or the activations or what. You know what I mean?
I think mostly the data. Like there's also like the there's Adam Brown who's like kind of pushing back against all of this and saying, what if like I don't know, invention of general relativity is just interpolation on a grandiose level of abstraction.
Yeah, but I feel like that's very like I think the problem with all that is interpolation of what? Like, are you talking about some abstract ideas? Like I think on neural networks, we actually have some geometry, and there are some things where you can talk about interpolation in like activation space something. But here, if you talk about relativity, you're talking something about I don't know interpolation in idea space or like maybe you're talking
like
about. You could take out the data and talk about interpolation in I don't know string token space, but then it's very doesn't make much sense. Because the things, if you talk about general relativity, you're talking about something more like idea space, like token space, because like one thing is isomorphic for the other. Like one thing is related. You can get it from the other, but it's a very complicated map. Like two sentences that are very close in, which tokens they have can mean very different things and be the very different ideas. And
I think, I think Charlotte also makes this argument actually. Like most of these people are like Platonists and say that this is interpolation or extrapolation in a Platonic space, basically. So space of ideas essentially.
I feel like Cholet is also super vague about that. It's not, I don't know. And you can see about how Cholet is very vague and doesn't actually have a real idea of what kind of interpolations he actually means and what things it can do versus it can do. That's why he keeps making new arc things, right? He doesn't have a thing of interpolation is totally incapable of doing this thing, therefore there is this final arc that if it's solved, I was broke out. It's not. It's just basically just finding things that LLMs are empirically bad at and saying LLMs intelligence whatever. It's not saying a much bigger thing that's not actually about anything, any math of interpolation. It's just some vague vibes-based argument about generalizing to more things or whatever. And it's like I just said this whole people talk about interpolation exploration feels like super vibes-based from the end, and it's never actually about any specific formalization of what it means normally. You find that the people are just using it. It doesn't make sense because people are just using intuition for like 2D things, and they don't make sense on multidimensional stuff. Like there was the Lecun paper about everything is
that one is formalized. Yes. That one actually uses formalism, but given under the definition of the convex hull of everything is extrapolation in neural network. So That's
Yeah, I
kind
think
of
they
yeah.
don't really make like the problem is once you start doing something more formalized, this kind of argument starts to either not make sense or becomes more complicated, and people don't actually do that. They just are on the vibe interpretation of just saying vaguely, like using the word extrapolation as a metaphor or something. But anyway, I think I ranted enough about this. Let's go back to the paper.
I feel like this
yeah.
could be like a
Go ahead.
tool like a parameter decomposition if it's like used.
Sorry, can you repeat that?
A attribution parameter decomposition. APD.
Attribution parameter decomposition. You mean the? Oh, you mean this one? I think I found the less wrong post.
Yeah, I don't know what attribution parameter.
I'm also not familiar with this exact method.
Or it just feels like a similar-ish thing where like it sounds cool, but not many people use it.
Oh, like that was your example for that. Okay, I see.
Maybe.
Yeah, I never heard about this method, so I don't know.
I do feel like I do think it's true that you can do some cool toy things here, and you maybe learn something about how some model represents some things, and feels like this is good science of some interpretability things about representations, but it's not
Minimizing
useful for
yeah.
steering in practice, because it's not like we haven't found the the shape for deception or whatever. For that kind of thing so far, just using linear things are okay. Like I wonder if can you use some fancy manifold thing to do something actually useful about the kind of things people try to use steering for.
Well, you can use it for steering, like in this paper.
Yeah, but
on the existing stuff you found so far. But I have this hypothesis. There is something like SAEs which can learn arbitrary like shapes in unsupervised way, that it exists in the architecture space, but we just haven't found it yet. Or someone did it and I just didn't see it.
Possible, but at the same time, there's definitely something like that.
There's a whole field of manifold learning, which I was directed
happen
to.
If you know how NLAs use like language models as the encoder and decoder to like reconstruct activations? For your idea, are you suggesting we use diffusion models as the encoder and decoder for the activations, and then train on the reconstruction loss, like image models?
I mean,
that wasn't my idea.
Yeah, is that your idea?
Also interesting.
But I think
that
this is related to that.
Yeah.
We do have. I think that's the thing I was going to say, that we do have something that does find arbitrary shapes. It's called machine learning.
The issue is the shapes of machine learning is this billion-dimensional, incomprehensible mess of matrices.
I guess maybe you can. So the thing with you might assume that they are simple in some ways. I mean, that's also machine learning. Like, it feels like maybe the problem is the shape. The actual shapes are very complicated, so you are not going to find a method that makes them. I guess you could.
There is this whole field called nonlinear. Yeah, like there is this whole field called nonlinear dimensional reduction, which also is called manifold learning, which I was redirected to when I was thinking how to falsify people telling me that you need extrapolation by extrapolating from a manifold, because I was skeptical like you that there's no empirical basis for these vibe-based arguments. And I eventually converged to this nonlinear dimensional reduction or manifold learning field. So maybe in this field there are some concrete tools that you can use to, in unsupervised way, find manifolds in arbitrary data that are interpretable because they are dimensionally reducting from the billion parameter LLMs to 3 dimensions.
like the nice, like what you want is so I said the thing with LLMs, but the thing with LLMs is you are trying to find the shapes that I don't know produce the correct text or something, and that's a billion dimensional shape or whatever. But here it's it might be tractable in that you have the machine learning model, and what you want is decomposing a set of smaller shapes. That means
Yeah,
the
yeah.
independent things. So maybe that's a tractable problem.
Yeah. I think, and there's so much in this field because neural networks are not the like if you take neural network activations as a data set, that's like it is like a data set of extremely dimensional numbers, and you're trying to find patterns in it in Mech Interp basically. So, and there's many other fields where you have I don't know, in physics for instance, like where you have so much data which is unstructured in so much measurements, which technically like a lot of features, if you use features, I use the word feature in the old school machine learning sense, inputs.
I would say in a lot of the hard science cases that you're talking about, though, there's incredibly strong inductive biases that you can use. Like you're pretty much
Yeah, that's also true.
you're pretty much able to just figure out like most of the time you're basically just assuming that the majority of the variation that you're dealing with is just random noise that you don't have to care about. And here I feel like it's a lot more of I think it's a lot more of a superpositional issue, because if you're thinking about a lot of the nonlinear decomposition techniques, like if you think about, a standard one of those would be something like a UMAP. And like UMAPs
Yes.
can obviously reduce dimensions pretty easily, but
But
what
UMAP
you're
does
actually
not really.
sorry, go ahead.
I feel like UMAP sometimes like gives patterns when there's none, though. That's the problem.
No, I agree. That's fundamentally kind of an issue, which is like it does well for like showing patterns within local structure to some extent, but the issue is not necessarily that. The issue is you're basically having to decompose a very, very large nonlinear structure into a bunch of smaller nonlinear structures, and that's where I think it is somewhat like it's going to be intractable if you're trying to do it in a completely unsupervised way, which means that what you're looking at really is an inductive bias that allows you to separate out useful shapes, right? Because
At the same time, I
yeah,
will expect the machine learning to want to learn random patterns. The reason you can find these kind of shapes already on the things is that there is that great set has some incentive to find simple shapes that to represent whatever thing it wants to represent inside it. It's not representing random things. That's why you keep finding, these kind of curves, because they are just they as simple as they have some nice properties of how when it wants to represent some 1D variable.
I just realized that someone in the old Anthropic paper, old, 1 year ago or something, when they scaled sparse autoencoders to I don't like big model Haiku first, and they threw UMAP at the features of SAEs, they found some clusters there. So maybe some of these clusters could be used as basis for manifolds.
And I guess you can think of sparse autoencoders as a way of doing this kind of thing we're talking about, but they just assume that they have the inductive bias of assuming that everything is a linear direction on the space, all the features.
Yeah.
So maybe you can get better by just still making assumptions, by making assumptions that it's some simple, that the representation are some other simple kind of, I don't know, low dimensional manifold or something. And that's your inductive bias that helps you find the thing. You have some assumption that is more complicated, that is just linear, but not arbitrarily complicated, because then you get into you need machine learning to find this sense, and then you can't understand it, and it becomes intractable.
Yeah.
I mean, the reason
Yeah.
machine learning works in the first place is also because it assumes it's simple in some sense, that it has some inductive biases of the transformer architecture and all that, but still. You probably don't need to get that complicated. There's probably some middle ground between fully arbitrary, functions and just lines. Like,
You know, like still the features in SAEs, yeah, like are like, they are. If you do SAE steering, you are steering linearly. Why cannot we like look at the UMap of the SAE features and see? Oh, it looks like this and do like, I don't know. Maybe there are ways which is like you look at this 2D graph and you automatically maybe find some shapes potentially. Somehow.
I mean, there is ways of doing. You can do the spline thing with PCA, but that
Yeah.
they do here. But yeah, does that is there a nice way of doing just person encoders, but you assume everything is a curve? That's not true because we already have an example that's not a curve on the thing, which is actually like a 2D thing, but.
Well, you can say arbitrary and dimensional manifold
Yeah, I think
in
if you
general.
get it has to be low dimensional to not be intractable.
Wait,
but,
I think. Wait, I'm not sure if manifold is actually the correct term because manifold is a space that resembles Euclidean space near each point. So I think it cannot be like, it cannot have holes and stuff like this.
yeah.
So
I
arbitrary
think it's
topological space.
It's kind of a vague. Yeah, I think manifold is probably not. I think I seen people complain that people in machine learning use manifold in a very vague way sometimes, that is actually technically not true. That is approximately a manifold some things, but that are not actually a manifold because they have holes and all that.
Yes. So maybe you could have something like SAEs which don't just learn a single point, but also try to find these shapes somehow. I don't know how. Maybe it already exists.
Yeah.
Like UMAP finds, like if you do SAEs, then you do UMAP. That just does dimensional reduction on the extreme dimensions. Into just 2D. So there you could find 2D shapes. But you could do also UMAP into
I feel like you
3D
just need something
and find
where
3D shapes.
you find something like you restrict the model. You could do maybe you can do something where you try a space something else person encoder, but it has a bottleneck when it has to represent with some simple shapes, like maybe low dimensional manifolds or whatever, the data, and you just train it to reconstruct with that bottleneck instead of
Yeah.
doing
Exactly.
a linear thing.
Like right now in SAEs, you just collapse everything into disconnected points with sparsity. That's it. Like that doesn't have to be the case. I think. Or like you can also, but I'm not sure. Yeah. Like if you did SAE,
Although, if
like
you
you
want
could
it
do
to
a toy
work
problem.
efficiently, it better be something that you can do with some simple matrix multiplications or something, because otherwise your GPU is not going to like it.
Yeah, you could test this on a toy problem actually. Like you have a data set which is just a circle. I guess the neural network itself will just learn it without super polysemanticity insanity, probably. I don't know. If it groks. Or something like that. And you could train SAEs on that.
Have you guys read the Goodfire paper on this subject specifically? I think it's called like scaling SAEs in the presence of feature manifolds.
Oh, nice.
Wait,
no, I haven't.
That sounds very related to what we are now talking about.
It was a couple months old. Yep, it's this one. I'll send it to you. Where's the chat?
You can also put
Yeah, I
it on
found
the
it as
reading
well.
group channel if you don't find it up there.
Where is the chat?
Essays model the activations of neural net as linear
Oh yeah, no, that
combinations of
is not.
sparsely occurring directions of variations. The ability of essays reconstruct activations follows scaling laws with the number of latents. In this work, we adapt capacity allocation model from neural scaling architecture to understand essay scaling and in particular to understand how feature manifolds influence scaling behavior. Consistent with prior work, the model discover distinct scaling regimes. In one regime, feature manifolds have pathological effects on causing essays to learn far fewer features in data than there are latents in essays.
So I would say this one I think is pretty good in terms of like they don't really try to professionalize this or formalize this as much as it might be as nice, but it could be cool. Like it is definitely the case if you could build some sort of expansion contraction algorithm where you use some sort of inductive bias, like we've been talking about. SAEs have a linearity inductive bias, but maybe there's other inductive biases that exist where you can just take linearity inductive biases to sort of split apart a structure and then consolidate, and then you like fit nonlinear structures on like the smaller linear chunks essentially that are created from the manifold, and then just like do that over like iteratively. It might be possible to do something like that, but I haven't I've thought about it, but I haven't thought about it enough to where it would be an experiment that would be able to be run. So yeah.
Makes sense. So yeah, I guess the running UMAP on the sparse encoder feature is like a subset of that, right?
Yeah, the
by
UMAP
the way,
still
there is
doesn't.
How CCH be more reliable though?
on the paper, by the way, there is another
Yeah.
sample we haven't looked at yet, which I think seems interesting. This is like manifold steering a visual board model.
Oh yeah, I really want to know what exactly is the example.
Yeah.
Recurrent worm model. What is recurrent worm model? Probably not recurrent worm model. Schmid-Huber cited. Oh yeah, Schmid-Huber happy in his in his room. I wanted to say grave, but he's still alive. What the hell? Okay.
You are jinxing him.
Yeah,
He's going to
well.
die tomorrow now. You'll see the news and it
Oh,
will be
no.
your fault. Such models of geometric structure, manifold by steering could be... Okay, so this is cool. This is the thing I was wanted to see before that I mentioned, that seems like they actually found a thing, looked for an example in a thing where other paper hadn't found the structure yet. Which, if they did that, is cool.
Yeah.
We train a recurrent work model on the model. What does that mean? Classical control tasking and task. Yeah, so this is the mountain car thing.
Okay.
It's a typical simple reinforcement learning thing where you.
Yes.
There is a car and it has some. I think it has some wheels and they have to move or something. I don't remember what it looks
It
like.
has position and momentum. I think it doesn't even need any wheels or something. Like the only thing is that position and velocity. So
Okay.
not even momentum. And just go right and left. So I guess right is like increasing velocity, basically. I guess that would be my guess.
I have no problem.
Yes. There's a figure. Do you want to check the figure? Oh, it's okay.
Yeah. So it can move, and it has to get there. And if it moves in this direction, then it stops, and it has gravity or whatever, so it does that. It makes sense.
Yeah.
So
Okay. This is simpler math compared to the previous math. Yeah.
Okay.
This is just normal machine
So they
learning.
have a convolutional neural net. And yeah.
And why did they say a recurrent? Oh, gated recurrent unit. Okay, so that's a form of recurrent neural network, alright.
Position to play the role of the concentrated domain.
Hey, Alpha.
Hi. To start, we collect encoder activations from a lot of the activations. They observe that they could be occur, but they still observe on the manual way probably.
Mm-hmm.
They look about the PCH until they find the thing. We parameterize
Yes.
the manifold by partitioning the position range into bins and fit a smooth spline through the bins. For a given input, they compute distribution of the positions, insert the distance of activations to the center for each position.
The output distribution of the positions.
Also, by the way, Fit to Fire, if you want to work on this and your problem is that maybe the Woodfire people will do all of everything, maybe you should just apply to work on Woodfire and go help them do that.
I
Yeah.
had some of these thoughts as well, but yeah, I need to do some projects first to. I don't know.
I also think of like should I should apply it to Tropical Fire or something, but
Or we'll get Discord grant.
yeah, maybe we should
Or
probably
maybe
have applied to
combination.
more grants. I think there was one that the deadline was this weekend and we didn't send anything for that.
Oh.
Kind of forgot, but there are more grants, I guess.
Hmm.
Although that one was for a project,
Yeah.
and I don't think I mean, I have some ideas, but I feel like these days I'm keeping like I'm iterating pretty fast in like don't have any project that I feel like I'm super confident on, and just trying a bunch of stuff a lot with help of cloth code. I just kind of not liking any of them, and I keep switching projects and not actually finishing anything. Maybe I should focus on something, but I still I don't know. I don't feel like I have anything I super interested on, right?
Yeah, we have the same exact issue basically. But I don't finish
I feel like
the
it's part of
steering vector.
improvement because some of the things I did in the past was actually focus on a project, but focus on the wrong project and waste a lot of time. And now it's faster to check it with Claude, although I don't trust it that much when I'm doing things fast with it without revising it very much, but at least for some getting some idea of some pages that sometimes it helps. Anyway, so they have this manifold. They have got activations. They seem to be a one-dimensional thing, which makes sense because they're a one-dimensional thing. It's another curve. They do a 1D smooth things. At the same time, okay, this is a new example. Same time, it feels like this is a simple problem where you have some you picked it because they have some reason to expect that it will have this structure because it's just a one-dimensional thing.
No. Wait. This is just reinforcement learning. Therefore, this is shape out of not data, out of just reward, right?
Yes.
Predict frame.
But
Well, technically, the data is the physical environment, but still.
But the thing is that physical environment has a linear thing, like it has a linear structure, okay? Like it has a one-dimensional variable thing, and it makes sense that you will represent it. And,
okay, yeah, that's true.
And actually, what is the thing? I'm curious what the behavior is. So position to play the lower the question, but is position? Wait, I'm confused. Is position an output or an input?
Environment, so it should be input. Output should be just the action, which causes more input.
Okay, but
That's my understanding.
then the behavior, I'm confused with behavior manifold. What is the behavior manifold here, though? Because the conceptual domain said is the position, right?
I guess you can change the position, and that will change the neural network as well in the input.
Yeah, but the position
guess
is not
it
a
can be-
behavior, it's an input, right? So like
I
but
mean,
then
the position has a
steering
manifold.
does-
So if you change the position in the input,
partition the position range and beams.
yeah, for a given input, so they do it from input.
Very consistent with,
The output distribution over positions. Wait, so maybe the modeler also predicts positions. Also, hey Alpha, this is an interesting paper, which is like formalizing a lot of the different shapes found in all the different models.
Yeah.
And also doing
it's
some
doing is
experiments.
trying to do a steering on them.
Yeah, and also doing the manifold steering on top of them. Because that's more efficient.
What is manifold steering? Like, how do you?
So if the shape is a circle, for example, then you like steer on the circle instead of just steering in like in a straight direction, like a lot of steering vectors are doing, basically.
Yeah.
You respect the
So
geometry of the
instead of-
representations.
Instead of trying to find, like here there is a circle and it's like on the activation space, and there is different points representing different days of the week. Instead of steering by finding a Monday direction, which will be linear steering, you take this Monday direction and take the opposite, and this kind of doesn't help that much. You try to find this circle that represents the days on the week, and you kind of move along the circle to do a steering. Like you want to you can do a smoothly change between one day and another by doing rotations on this circle or whatever.
Yes. I wonder if
Or
you could do
here
this
they
steering
have,
on mouse. Since
Well, this kind of
mouses,
this feels similar to like the
Maybe.
word to back of how you were able to steer like king minus like queen equals main or something.
that's the linear though. You are steering there. You're just adding the vectors
Yeah.
in straight lines. So that would be just normal vector steering. Corresponding.
Yeah, but I'm saying that if you're able to
This is
do that, it
correct.
makes sense. It makes sense you're probably able to draw circles in the space.
yeah.
Yeah.
There
Okay,
should be
yeah.
in word to back, there is also circles because there is that of the we saw, like there are
Oh yeah.
because different days are more likely to be close to the second one. For the same reason that there is a circle on the paper also showed there is a circle on probability space of the outputs on the days of the
It's a
week, for
circle,
example.
not an ellipse. It's a circle, not an ellipse.
It's a kind of complicated shape. Like for the days of the week, it's a kind of circle because the last day connects to the first day. Like it wraps around.
But the radius, there's no radius equivalent
You
for
mean,
this higher
sorry, I
dimension.
was thinking serious. It's kind of a circle-like shape.
Yeah, so it's circle
Circloid.
light. Yeah. Yeah, it's
Is
probably
that
like
a
It
word
has
for
to be.
circloid?
It's more likely to be. It's some weird curve. It's more likely to be more like a circle than an ellipse, though, because if it was an ellipse, some days will be more separate than others, and the model wants to have them be the same distance.
I think P circles is the generalized circles only. Like in general,
wonder-
it's a spline in infinite dimensions.
What is the manifold
in
shape
with
for
in-
numbers? Or does the model
For
Can you say
or does the
numbers,
model have any like or does like the model like I don't know, digits of pi?
if you have some number variable, is probably, and it's one dimension, it's probably going to be some kind of curve.
Yeah, it's probably
Yeah.
have it.
Like the spirals on the line break task
Yeah.
or whatever.
Yeah.
Like
But here is an
and Ellen,
example where it's like a graph, like it's a 2D position in a graph. Like it's like there is some 2D map and there's a position on it, and it the model represents that as like a kind of 2D shit that is wrapped around.
Well, the numbers are a helix from the Max Tegmark clock.
Yeah.
Since LLMs also use
That's
trigonometry.
yeah. That's still a kind of curve, with more dimensions.
Yeah, that's true. And helix because it just loops like this.
Yeah. That's
And Goodfire
because-
just rediscovered this.
that's because the numbers wrap around it. That it has this variable where the numbers, where the same digit has the same, the different number has the same digits, and in the but they has to get traps when it keeps wrapping around, so it needs a third dimension to keep.
I wonder if there's a
going.
setup. I feel like not just the circles. I'd be curious if you could like figure out ways to train different facts to be a circle.
I think by making the training data such that it's in a circular statistics. That's one way. Another way would be somehow for the model to infer that it's useful to somehow represent it as a circle. I don't know.
Yeah, but like I feel like if you could show that like normally it doesn't do this, but in your specific data set case it does, that'd be interesting.
Oh, okay, I see what you mean. Yeah,
I'm like trying to I'm trying to say like intentionally causing it instead of just observing it, because like this feels like observation. And like if we know exactly what causes this, I feel like they'd be interesting.
Yeah, like one paper was trying to find the cause, and it was in big part that it's also in the training data that if you map the statistics, do some linear algebra on top of it, you found out you can recreate the shape as well for some cases.
What's
like
that
the
paper?
days in a week.
What's that
And
paper
also it
for the
was
days in
only
a
for Word2Vec, so it's not for LLMs, but it's close enough.
Yeah, what's
How was
that
it
paper?
called? We had it on a reading group some time ago. It was very mathematical paper.
It's not just for Word2Vec though. Like it generalizes to like they use it. They talk about Word2Vec, but the reasoning they did, it seems to me like it just generalizes to any matrix that.
Yeah.
Anytime you want to have some points that are close to each other, if you want the cosine similarity to be similar, that's why it's a circle, because like it only matters.
I mean like that makes me also curious if you could make facts that were originally not a circle become more circle through fine tuning.
Yeah, I think you can by shaping the training data or somehow other incentives.
I want to measure that. I want to measure this. I want to measure that.
I feel like a lot of things are just going to be circles. I think you're going to have trouble finding one-dimensional variables that are not kind of.
But like it'd be but it's interesting if I find the things that are one-dimensional and then show that I turn the one-dimensional into like the helix shit.
No, I think most one-dimensional things are going to look like a helix, though. I think you could take a helix and make it into a circle by giving it a lot of examples that the last thing is connected to the first one, right?
Yeah,
like
the modular edition.
Yeah, you have a bunch of examples. Experiment you could do. You train a model in addition, right? And then you fine tune it in modular addition, and it should have a helix that becomes becomes more like a circle when you train it.
Yeah, that's the simplest example. I would expect exactly that. Yeah.
It might not be exactly a circle. It might be just some kind of other helix, but like the ends are connected in some way. But yeah.
Do they get better results on mountain car?
I should go back to the mountain car thing. The mountain car thing is they do steering on the mountain car thing, I think, in some weird way, but I still don't understand it. Let me actually figure it out, because I'm confused by the fact that the thing they're the behavior here is also the position, but it seems to me that that's a. I guess you can talk about a position of where the card is at the later. Okay, let me read it a moment. Sorry. Also, is the
Linear paths, manifold paths.
is the thing also predicting the?
Yeah, it looks like it's also predicting the next frame, so it's also predicting the position, right? X is just position, right? It doesn't mean anything else.
Yeah.
Okay. Yeah, so it's in reinforcement learning there's the terminology that I forgot that I think it's wormhole based or something like that. I forgot the name. Where you also predict the world and not just actions. There's a terminology.
The model,
for that.
okay, the model outputs a frame. The model outputs an image actually. The output outputs an image given the previous frame as an action. So this is like a predict the next. This is not an action model. This is a video model. Like this is a card model that is trying to predict the next card position from the current position and action.
Oh, okay, I see. Yeah. And ground truth is physics simulation.
Yeah. So it's okay. So I can see how the position, if you get the position from that, the output can be the position. But then it's just the kind of same of example where the right it's the output is the position. So it's it makes sense. Like it's kind of analogous to the other ones. I kind of will want to see some reinforcement learning thing where the output is not the same as the thing is represented. Like all
so
of the
it's not
examples on this steering paper has the problem that all of the examples are about the steering.
But it's still predicting actions. Oh, wait, so is
no the output
so
that's
the
an input. Yeah.
It's just so input has frame and output is frame and action.
No, input is frame and action, and output is frame.
Oh, so
it's
it's
playing
not
on it's playing here. The model predicts the next frame given the previous frame and action. It doesn't output actions at all. Yeah, so it's another example of the same kind of thing. I feel like this whole paper has the problem of they just have examples where the thing that is represented is just the output of is either the output of the model or directly related to the output of the model, right? Like the best one, the one is this one. This at least is the current position and not the next one. But it's still very simple. They don't do any intermediate. Don't find any intermediate variable or anything where the model is represented as thing that gets done some complicated operation on it, like the length of the sentence, or for example, for the linear representation hypothesis thing. There are examples where it's also the reason why they are this way. It's also just the statistics of the thing and not the other the other explanation that we talk about.
Geometric rotating. Line breaking.
I
really want
to make
see
a
this
less
on the line breaking.
Because I see that the good fire people are also getting it's all statistics idea, and I don't think that's true, and maybe it's not obvious, and maybe I should write about it instead of kind of assuming that people will figure that out. Like I'm sure other people
exposing good fire.
No, it's not the problem with fire. It's just I feel
exposing the whole Mech Interp field.
I kind of expect a lot of people to agree with me though. Like, yeah. So far, I only seen it on this paper, but I kind of want to see what the literature they cite here for the statistic stuff said, and there's a lot more people are saying talking of with this was just the statistics of the cells. I mean, there is some sense in it. Everything is the statistics of cells, but like the specifically the other paper was talking about bigrams basically. And first, showing isometry with an presentation episode.
I don't know, the word statistics is so weird to me because it can mean some people just mean like co-occurrences, which is falsified in general.
Okay,
I think.
so I think statistics like doesn't actually just mean concurrences, and people are just
Yes,
confused. Like
that's my take as
statistics
well.
is just the math of finding things from data. But okay, there
Yeah,
is a more some colloquial way of statistics where you talk about simple statistical measures over
Like,
the data, like the mean or whatever, and call that statistics.
Yeah, like yes, exactly. Like when some people say LMs are just statistics, then I see people that have no idea about how LMs work. Right in fucking New York Times or something, I saw an article where someone was like talking about image models, and then he started talking about how they work, and my brain jumped out of my skull because I read that diffusion models are just taking averages of the pixels, and yes, that's how they
Yeah,
work.
that's not how it
Anyway,
works.
I'm like, ah!
Yes, statistics is very vague, but I think there is a I think people shouldn't just use the word statistics. I think if if you go to the dictionary or to Wikipedia, the actual meaning of statistics is vague enough to mean nothing, and often
Yes.
people here use the vague meaning and then get confused because they mean the more colloquial meaning that is like the kind of statistics that you learn in high school, and
Yeah,
or that
that's another.
people use in science. People in science usually use very simple statistics, like calculate the mean or
Yeah,
do p-values or whatever, and you don't or
also I
only
see cases.
correlation.
Yeah.
Or other people just mean it's only correlations, but the statistics also includes like causal, the Judea Pearl stuff is
Yes.
also subfield statistics.
Yes.
But
Yes.
yeah. I think the version
And-
of machine learning can only learn correlations is also wrong, but it's wrong for more interesting reasons. But I won't get into that. Let's finish the paper first. We keep getting this study is also like very late now, like it's being 3 hours or
in.
something. Yeah. Geometry aware steering reveals shell structure of behavioral representation.
Strictly positive.
We show that the steering representations along geodesic from M includes smooth, coherent transitions in behavior that follow geodesics on M. Thus, we show that optimizing interventions to produce behaviors from geodesic programs.
Oh.
Yeah, I think this all is cool, but still I have problems that is very only applied to very simple thing, to a very specific kind of problem, and that doesn't. Maybe it's there is some pathologies of linear steering that maybe would be better if we found the geometry. But how can we actually find the true curve, the true geometry of things, and how much maybe linear steering does work often. Maybe often the things are actually just represented as a line or some direction, and there is the other thing of even if it's not represented a direction, if you have a manifold, you can decompose it in a bunch of points with linear directions, right? Like in all of the examples on these papers, you could do the same with linear steering. You just need a lot more features.
You mean like if you have a lot of features, like you basically fit lines between the different features, you mean?
Like
On
here, for
the-
example, instead of having this, you could just have steering for examples. Like, yeah, they're doing linear steering and this breaks, but it breaks because they are doing linear steering on this point, right?
Okay.
But if you do linear steering with, you could imagine finding the direction for this square and the direction for this square and so on. With a lot more features, you end up having the same effect. You just need to pick the right.
Maybe for something like real number addition, this wouldn't work.
Yeah, but that's
in general.
real number addition is not a thing though. Right.
Yeah, I guess, yeah. I guess you could just have billions of features, as in what your floating point allows.
A more philosophical hot take that the real number addition is not actually real. It's
because infinity doesn't exist.
yes.
Yeah. I see what you mean. I sometimes hold that position as well, but recently I'm more fluid. Not
I
that
don't know. I
finiteness needs
don't.
to be more
I'm not
finitenist.
actually that confident of that. I just kind of
Okay.
was half meme. But I mean, it's
Okay.
not, I don't think you can do it in real life. You can do.
Yeah.
You can do finite.
Not in
simple
computers.
You can do not in real life in general. I don't think
Mhm.
like physics like there are limits of how much information can be on a volume. I don't think you have infinities in there. Like if
You
there
can
is
just
some...
you can just approximate it to a certain level of how much energy and computational power and so on you have to compute it.
No, I think you can, like, there is a point where, like, if there is a continuous thing, is maybe the quantum wave function or whatever, but like the actual things in our universe are all discrete. Like there are a maximum amount of qubits on a volume. And if you
I see.
more information, it collapses into a black hole. So it has to be like I don't know what the correct way of thinking about it is, but maybe Wolfram is correct and there is some graph thing or whatever. But yeah.
Yeah, I think the Barkenstein bound.
Yes, that's what I'm talking about.
What you were talking about. Yeah, okay, yeah. That's for both thermodynamic and Shannon entropy. The limit for a region of space with a finite amount of energy. And therefore finite amount of information. Yeah. But Wolfram's model is discrete though.
Yeah.
But yeah, like they are continuous models. Also, apparently there are some models that
there are
assume
continuous
actually
models, but there are no continuous models where you can actually interact with the continuous stuff, right? It's just continuous stuff that for all practical purposes is discrete because otherwise it will break thermodynamics.
Yeah. Or you assume that the continuity is on such a small scale that you cannot measure it and escape the falsification hammer, and you win, and lose because your theory isn't falsifiable.
No, you can't, in general, the best thing about me is you can't have more than a certain amount of distinguishable stakes on some space.
Yeah.
There's also related
Like,
to if there was any, like, there is also a limit of how much you can change distinguishable bits of information. That is like the Landauer principle, also because thermodynamics. So like that also means that physics can't be using also arbitrary levels of information to do things.
Yeah, that's also
Anyway,
to the
let's
computation.
go back to the paper and finish it and then stop recording. And
Yes.
maybe keep talking about other stuff, but I keep distracted. Anyway, so pathologies of linear steering. But it is true that it can be impractical on the numbers thing, for example. Yes, you could find a feature for each number, but this is not attractive. This makes the model seem a lot more complicated than it is. And it would be better if you actually found a nice curve that explains all of the numbers. And then your explanations of the model becomes more compressed and smaller. Like it's a better abstraction.
Wait, what is your point again?
I'm talking about, okay, so if you imagine, I don't know, the helix, right? For the Max Therman paper, you could train a sparse encoder on that model, and it will find a feature for 1, a feature for 2, and a feature for 3, and so on, right? But if you try to explain the model, it actually might, I think it will actually find the same thing as Entropic paper. It will find a feature for this model has a, like this number ends in 1, because they are all in the same direction, because the helix keeps rotating, right? I will be find another feature for each of the numbers, like each of the second digit, because it wraps around. So it's the third dimension on the helix. So if you try to explain the model as an attribution graph over that, it becomes a super complicated thing that's very confusing. Right? And I think there is
Wait,
actually,
the attribution graph, you mean
it's the
in
Anthropic thing where
addition?
you
Do you mean the addition circuit, or
yeah, I mean the addition circuit. Imagine you have the addition
Okay.
circuit. I think actually
Okay.
this is actually what happened in one of the plots in one Anthropic paper, the Anthropic paper attribution graphs. There is a graph that it is overcomplicated.
because it just dissected everything into
Yes,
all sorts of abstractions?
like there is one about addition. I don't know if I'll find it.
Yeah, I found it in the circuit here.
Yeah.
Yeah, or you can click on addition on top.
Yeah. So.
Someone joined and left, I think. Okay.
I don't know. So looking at, you can do something like this, but it's true at the same time that instead, this kind of explanation seems overcomplicated. I expect there is some nice explanation in terms of geometry of it.
By the way, this is also interesting. There was some other paper saying that that they found multiple circuits that are causally influencing the behavior, but there's multiple of them, so there's not one circuit, which makes sense, I think.
Yeah.
I'm not sure if you've seen that paper.
I don't know which one, but I know there is a bunch of results like that, right?
Okay.
People usually
it's
find
not the first one.
the circuit. I don't remember, but yeah, I think generally a model. If you see on the attribution graph, like they also find that a lot of the things have multiple paths and there are different heuristics, and the model is not just have a neat single way of doing that, of doing a thing.
Yeah, like yeah, I think
Yeah,
the point
and
of
also
this...
the results where if people try to find, people delete some circuit from the model and then it's still doing the thing, right?
Yeah, you mean, I think I know what you mean. Some adaptation. I read that in Newland stuff.
Set geometry of behavior and representation come from.
Are you looking at what I posted? Or no, at
No, I
the
was
paper.
going back to the paper, sorry.
Yeah, good.
We
That's good,
don't,
actually.
they don't study the origins of the shared geometry between behavior and representation. I mean,
I keep talking
think
and not going through the map. Okay.
I feel like this a lot of, I feel like there is a thing here where they pick examples where there is a shared geometry within behavior and representation, and there's a feature of the examples they chose, and there are other examples where there is not, and like their methods requires them to find a geometry of behavior. And the methods where there is a geometry of behavior, there is going to be a geometry of representation somewhere in the model where that represents probably the activations of, like when the model is going to output that or whatever.
Yeah, like
Okay.
in AlphaGo, for instance.
Well, that studies
or
shape the
like
geometry
RL.
of neural representations that
Yeah.
they cite the other papers. This fails to explain how geometric structure is forming out of distribution inputs. Okay, yeah, that makes sense. Encoders learning tasks have synthetic geometries that input tokens in context termini that's really different for the being learned to training. I think they mean the. Representation of produce novel behavior. Wait, what? Let me just. But it's just the. This thing.
Okay.
I know. This I feel it's kind of but okay. Like it's not that much of auto distribution thing. And I guess in that yeah, I guess you could say that the fact that it learns the thing working out. This is kind of another thing. This is related to the separation and interpolation. I feel like people use in distribution and out of distribution in machine learning extremely vague and bias-based in ways that also don't make that much sense.
Yeah. Which is
As
then
just a fancy way of
extrapolation.
saying this is more similar to the training data, more different.
Yeah, like I also have this intuition that it's more like continuous than this discrete in distribution out of distribution.
Yeah, I don't think there is a super well defined what it means for like something to be in distribution of some data, but yeah, never mind.
Yeah, like in order to actually calculate that, you would have to know the distribution of the whole data set, which you know, but whatever is the full distribution, not
Yeah,
just
you're
the
talking.
samples.
You have to define it as like, for example, in text, you're trying to think about I don't know some platonic idea of all text or something that could be
Yeah.
internet text, or I guess you could. Yeah, like you could talk about what is generating the data or something, but then
Yeah.
is it really like if you could think of okay, so what's generating data here is the universe, and is this really out of distribution of the of possible outputs to the I don't know.
Yeah, I see what you mean.
So it's the
I think,
model.
like, I don't know, like there was this model like Tolkien trained until 1920. So if data until then, no new data.
I feel this
If you
like
could, if that model could find general relativity or quantum mechanics, that would be epic. But it's too small and dumb.
yeah, but I feel that if you talk about the distribution there, are you really saying anything? Wouldn't it be better to just say this is more like the data or something? Like saying it's out of distribution seems like it's just making it sound more fancy or something.
Like, yeah, like I was arguing a few times something like that, but more like that. I don't see any two concepts or results or structures or whatever as having absolute zero similarity. Like the trivial similarity is that it's encoded in a language we can comprehend, usually, for instance. So that's why also it doesn't make much sense to me actually.
Representation and behaviors. I guess that's all because we don't have partly because we don't have a good theory of deep learning, so that everyone agrees on. So we can't really be like, no, this doesn't make sense because the correct theory of deep learning is this and defines this as this, distribution as this or whatever.
Hmm.
But anyway, as such a model for representation and proof novel behaviors. Yeah, that's true. Establish a shared for representation of behavior on this novel in context related tasks. Yeah. Oh, you might like this. See the contemporary work by this paper for formalization of this claim.
On what claim exactly?
The fact that we are able to establish shared geometry for the presenting of behavior
Oh.
is novel in context learning tasks suggests that regardless of how training data statistics inform geometry seen in the model, the overall behavior is not computational at the stage.
Yeah, I think this is true, but not fully generally. Like, I think a falsification would be if you would find a shape in some self-play reinforcement learning which somehow doesn't correspond to the training data, basically.
Yeah,
somehow.
I mean, I think there is a lot of examples in that. The line break thing is an example in that. It's not.
Yeah, that's true.
But it can mean anything. Like, if you have a modular addition circuit, the model has representation size that are not relationships between numbers on the training data. There are intermediate steps on the computation.
Yeah.
In general, you have a thing that it has multiple steps. It can't have variables in the middle that are not representing data that was close in the whatever, right?
Yeah, okay. Maybe you could do some big brain galaxy brain mental gymnastics to
I mean, you can
make the
always
claim there as well.
You can always say it's about statistics though, because you can you can always say it's about correlations because causality is also about correlations.
Yeah.
But everything is just correlations between data. But with enough high dimensions or whatever. But yeah,
I guess in causation they always correlate because of the cause, you could say.
I think you can see causation as a set of conditional correlations. Very big table of if this changes and this doesn't change, then this is going to, the probability of this is going to be correlated in this way, and so on.
Yeah, that makes sense.
The causality is a way of writing that is a nice abstraction over that tells you that things only that this thing will change only when these other things change and not when all possible other combinations of things change.
Yeah.
There's a Lesbron post about this, but yeah.
I think on Wiki I just found a part where they wrote this view that it's not causality, but yeah, I don't know. Counterfactual. Yeah, okay, that's a rabbit hole that I'm not gonna go down.
Anyway, so
and all gets collected to other. Okay, concept centroids. I'm still going through some of the formalism.
this is because they are representing manifold.
It's kind of interesting that I'm much more empirical last few years, but I'm still gravitated towards the formalisms. Maybe it feels to me that the formalisms.
I should start writing paper reviews on Lesbron or something, but
I mean, you can do that. Some people do that, yeah.
Yeah.
So not just on Lesbron, but
after
you could make
the reading group.
You could be peer reviewer on some Neurips or something.
Maybe. I mean, I maybe I don't know what the qualification of that, but I did publish something in one of the conference, so maybe I could be, maybe that's enough to be reviewer on that one. I think it would be funny if someone, like if I can be peer review, that means that if you also can be peer review, we just need a third person who could be peer reviewer, and someone complains that some Mech Interp paper or something is not peer review, we could say that we could. If we all say it's okay, it's basically the same as peer review.
At least there will be some people peer reviewing Mech Interp that actually understand Mech Interp. Yeah. Activation centroid is just the expected value.
More complex domains. To illustrate the arguments, we focus on simple settings for which the concept of interest will have a defined domain. Our expected task suppose are the concept steps. Exactly. This is the thing I was comparing about the whole time. Therefore, the content of the geometry is directly displaying the outputs. Exactly. To further validate claims posted in this paper, future colleagues need to explore more abstract concepts, like refusal, syncopathy, and persuasion. For courses, all concept-wise, it remains to be tested whether conceptual geometry concepts can be inferred from behavior in a related percentage of the weighted flow. I don't think you can. I think the answer is no. Or like, if it is, it's in some overly complicated way where can be an arbitrary. The behavior can be an arbitrary function of that. So, like, there are we going to samples where some simple thing you figure out, and there are going to be samples where it's actually super complicated and you can really figure it out. So, without reverse engineering the full model. So, yeah. Moreover, in those complex cases, it's unclear that what are the right primitives for representation account. We might need a notion of dynamics over manifolds, a view of representation as an aggregation of several geometric structures. That could be interesting. Or perhaps altogether a different object. Even if geometry is the right subspace, maybe I should send this to Philosophy because it's even if geometry
Dynamics.
You like the
They
word
say
dynamics.
Yes. Wait, I need to find that section.
It's on the future work.
Yeah. Let me see dynamics.
Like the
It is unclear what is the right primitives. We made notion of dynamics over manifolds. A view of representation, aggregation
also
of similar geometric structures.
Bully, they also have your suggestion here. Like look at the fit in the geometry thing.
Well, we used a specific control protocol to fit. We note on fitting low dimension manifolds. Oh yeah. Operate hours to navigate the manifold. I see. An unsupervised protocol. This section seems to have all our notes basically.
Yeah. I mean, it's good that we can recover the notes because it means we understand the paper, but yeah.
yeah, that's true.
I mean, my main note is that the on this section, the answer is no, and they only some of the other stuff they find are only because they have simplified tasks on the way they explain here, and you are not going to be able to do this kind of analysis into actual tasks like refusal or whatever, or syncopancy, or even modular addition. Well, you can do this kind of thing on modular addition on the last, like on the modular addition model on the MLP. You can do it, but not on the attention. Like there is. I think often you are going to find that the models do have some representation of the output, but that's like on the last step.
Did someone try to steer the modular addition transformer using empirical methods? Like there's ablation for in the original paper, but like, did someone like try to edit the frequencies and see if it still works as long as the output is still coherent and so on? Did someone try to do that?
I mean, you can replace frequency. Like you can, for example, replace the frequencies by the pure frequency, remove the noise, and it works, and that works better. You can't change the frequency because you will need to also change everything in the model because everything is set up for some specific frequency.
Yeah, but could you do that still?
I mean, you can replace the model. You can replace part of the model by math that does the thing it is supposed to do, and it works.
Yeah.
But
did someone try to do that?
I think the paper does that. I mean, I did try that kind of thing when I was looking at the modular multiplication thing, and like of replacing different parts of the model by the pure frequencies version and seeing what happens. Like taking the math, like doing manually the math with the matrix multiplies of taking the embeddings as the pure frequency and like taking the other thing as like the weights, like manually writing the weights that will make sense if the thing like doing a Fourier transform instead of the I don't know, I don't remember the details, but it was something like that.
What I'm also thinking of is that like the input is just the A and B. So like in the middle of the computation, something corresponds to like some like I don't know a sinus W A and A plus
That's
B.
just on, yeah, but that's the in the embeddings.
So yeah, so if you could in the middle of the model, in the model of computation, just replace the A and B with some other A and B, and if the rest of the computation would correspond to the edited A and B.
But like the problem is there is no like okay, so the model is one layer, right? So the model takes the embeddings. If you replace the embeddings, you're basically doing the equivalent thing to replaces the input, so it makes sense. It will be the same, right?
Yeah, if you do it later, you are already corrupted the beginning, so it's broken.
And
Oh yeah, it doesn't work.
no, but on the let's say on the then you do attention, but the thing attention is doing is already doing the sign, like it's doing a different math thing with it, and like on that step you like it's doing the sine and cosine of the thing. Like let me open the.
Yeah, I can. This is. I have the screenshot. I'm looking at it right now. Here.
Yeah, I mean, I just wanted it to point at the things. So let me. So like on the embeddings, it's just the sign of and replacing is just replace the thing. The thing.
Yeah, that would be boring.
You can replace this. You can do this. I've done this. This works. I think Neil also does this on the Google thing, but I don't know.
Oh, really?
Remember. Yeah, I like you can replace parts of the model by just directly, sign of the thing multiplied by that,
can,
like, and do the Fourier transform to write it on the right place, and it's that works.
Actually, I wonder if you could just hard code an equivalent for multiplication. Just hard code it instead of training it and see if it will work.
On a bigger model, yeah, probably. But I mean, it's kind of hard to. There's a bunch of things like you maybe need to freeze it because otherwise Vincent is going to forget it because it's like going to be hard for it to learn that how to use it. There is a bunch of things like that. I don't think it's very. I actually had some time. I talked on Blue Sky and Twitter at some point with someone who was working on that kind of thing of compiling algorithms into neural networks, and they didn't think it was very useful in general. And I kind of agree. Yeah, but never mind.
Okay.
Anyway, I think we should finish this already.
It ignores that P light on a simplex. Oh, okay. So the Heldegger embedding is what creates the curve.
The most interesting control protocols will require manipulating intermediate quantities that mediate the flow of information from input to output. Give a small intermediate shape problems for splitting weight. Yes, but also that's in that example they should already realize why it can't be that everything is about the low dimensional statistics of the data. Although when they mean statistics, I will have to read the papers because they might be meaning more generally, but meaning more generally is kind of basically meaningless because just saying like the structure of the data. But okay.
Yeah.
Like it's basically saying there is something about the data that causes this.
I'm gonna put charger.
Oh, David Bao was helped with this, with your feedback and all that.
I don't hear you. Wait a minute.
Well, okay, so that's basically it.
Fuck. I accidentally put liquid
Oh, additional
everywhere.
results.
Oops. Okay, whatever.
They also
Wait,
test
I'm
a
just gonna
cylinder that has a wraparound.
Open my. Oh my god. I think I. Fuck. Okay, whatever. Can you speak?
So
No, I still don't.
there are additional results, and I found
No,
a cool
now
one.
I hear you.
There are additional results, and found a cool one because there's a cylinder. It's on the graph thing. They tried on a cylinder where it actually wraps around, and that
Hmm.
actually has the thing we will expect with the new.
Oh no. I'm not sure if you heard me, but I accidentally spilled water water
Don't worry.
everywhere. I think I have to clean it right now. Ah, damn it.
I'm confused.
I spilled a sweet drink, so now everything smells sweet. Oh well.
I'm confused because I would have made a wrong prediction here. They did a cylinder and at least from the image, it doesn't look like the figure is close.
What do you mean?
Okay, so if you look at my screen, I don't know if you're seeing my screen.
Yeah, I see.
Okay, so there's an additional result, right? So this is a 9x9 cylinder. That means that this is connected to this, right?
Okay. 9 cylinder.
Wait. Yeah. So. Oh,
So
it's
the
in the up direction. So it's wrapping around on this direction, but not this one. I think, right?
what is in context learning? ICLR.
It's
Is it
just-
ICLR also?
This is just the graph thing, I think. But there is a cylinder now.
ICLR is in context learning? No, it's the graph? No.
In context
What is
learning of
ICLR?
representation.
Because that's also, the
Yeah, the conference.
the
Don't worry.
Oh my
It's
God.
just this just they just mean the graph thing where they have
Okay.
a bunch of random walks and it learns the graph.
Yeah, okay. So this is the same graph like before, but now they tested 9-to-9 graph instead.
Yeah.
Okay.
Wait, is it actually in context learning? Like it's doesn't it learn the representations on? Wait, I'm actually maybe I was misunderstanding. I thought it just learned them from training.
That was my assumption or interpretation as well.
Yeah, but the way it's calling context learning is just a bad name, or does it actually in context learn different graphs? Oh, with sufficient context. Oh, cool. Okay, so it's not. So it's cooler than it's not that is you you learn trading model of a lot of random walks for a lot of different graphs, and then you can put a list of random walks in a graph, and the model has a representation of that graph.
Interesting.
Like, so it just learns to has this grid thing. I guess it just learns to map specific words to points of the grid, I guess.
Yeah. So like you can shuffle the input and it gets mapped.
I guess the input is just different, the same grid but with different labels, and the model just learned to map the different, to from a bunch of examples map it to the right to the same grid, right?
Wow. Okay. So this is actually ultra cool then. If I get it correctly. Can you also shuffle the inputs with the labels?
Yeah, no, they shuffle the inputs like I think the in context learning paradigm learns like it learns in context like what the.
So
where
this
the
is
labels are.
basically okay. I see. So this is
But there is
basically
a paper on it we could.
so this is basically like empirical evidence for a word model, you could say.
Yeah.
This is much better example than the Othello GPT example. Every time someone says LMs form zero representations.
I don't know which one it is. Or maybe it's this one. Yeah, I don't see the graph. Maybe, well, never mind. But in any case, in additional samples here, they have a grid. They have a cylinder, but I'm. Okay, so it is a cylinder, but I'm confused why. Okay, so I don't understand why it doesn't make a cylinder or something like that on the
Wait, so this
activation
is
space.
negative result or
So
no?
no, not exactly, but okay. So here they try a 9x9 cylinder, right? But the thing I'm saying is on this graph, it doesn't like on this image, it doesn't seem like this wraps around. But then I'm confused why like activation space, like these are not close to the like 0 is not close to the 9 0.
Maybe it wraps around since it's a cylinder.
Like
or
look if you look at my screen, like activation space
Oh.
not a cylinder. So I'm confused why that's it. That is.
Is there a link to the paper in the chat?
Oh, for to the paper, like it's on the events thing. You can find. Oh, never mind. It's since the event finished or whatever. It's not there anymore. Let me send it to you. I'll put it to the chat. Yeah, I put it in the chat. So, do you see what I mean, Burnie? Although, wait.
Yeah, that it doesn't look cylinderish. Like maybe it's just different
Like this.
perspective.
So some of oh maybe wait maybe it is cylinders actually, maybe it's cylinders, but oh no, I think it is. I think it's just weird perspective. I think it's just rounds around here. I was just confused.
Wait, so it even generalizes to this shape?
I think it is just trained on the cylinder though with different labels.
Okay.
Maybe I don't know. It will be all in context. I think that they don't explain it. They barely explain it. It will be cool if the model generalizes to other shapes.
It sounds like a paper on its own.
In context, you could do that. I don't think so. I think they just train it on the cylinder, and then it learns the cylinder, and then you have this cool map of the cylinder. But yeah, not that. Activation manifold is a mess. I wonder if this kind of shape is what happens when you have something where the two ends are connected, and then it wants to separate things, but then pull them together at the end, and it's kind of makes this weird shape.
That it wants to combine, but it doesn't combine.
Like it wants, yeah, it's like a circle, but longer, so it has to spiral more, and it does this weird thing.
Oh, okay. I see.
I mean, that's the kind of thing you can just figure out from the math, like from the similarity math, like the other paper did, like the Word to Beck paper did, but where they actually could predict the shapes very well. Oh, the authors of that paper commented on the YouTube channel of the Mech Interp.
They say.
Not that much. Which is just something. I don't think they actually watched the video. Just saw it on Twitter, on the internet.
Oh, okay.
They
Yeah.
just said that they hope that it was interesting, and they said generic things about their stuff about. But yeah,
I might look into that.
I can show it, but I don't remember. I responded to them, but I think I was kind of rambly at that point. I probably should have. I was kind of tired when I wrote it. I don't know if what I wrote makes much sense, but
I
uh,
see.
mountain car. Look how I'm being tired. I'm kind of tired. Maybe we should also finish already the streaming before.
Yeah, I think I'll look a bit more through the formalism